Recently, astronomers observed an extraordinary phenomenon that shouldn't naturally occur. In this mysterious event, 7 comets, each on a journey towards the solar system, are simultaneously heading towards our star. These clusters of ice and rock, arriving at quite significant distances from each other, will pass very close to the Sun over the coming months, starting from October this year. Such a massive approach of celestial bodies of this type has never been observed in human history. This undoubtedly excites scientists, as it all happens within a short period. However, the astonishing circumstance adding particular concern to the event is that during the same period, another astronomical phenomenon is observed. An object from a distant star system, named Triatlas, has also approached Earth in its closest pass. Remarkably, the probability of the simultaneous approach of 7 comets and this interstellar object is considered extremely low from an astronomical statistical perspective. It is highly unlikely that these events occur by chance. This suggests that the arrivals of the comets and Triatlas are unrelated and uncoordinated. But what if this is not just a coincidence, but part of a larger, possibly threatening scenario? Perhaps these passages are merely the start of a significant and alarming process. Tonight, astronomers invite all interested and curious individuals to listen to their analyses and assumptions about what lies behind this mysterious type of phenomenon, to understand what is truly happening beyond our usual understanding of the cosmos and physical laws. Don't miss out. At the end of the review, you will learn what these 7 comets are actually doing with our solar system. It all begins with the fact that similar phenomena, when bright comets occasionally appear, generally go unnoticed. In ordinary years, there is one, at most 2 comets, worthy of the attention of astronomers and enthusiasts. Time passes quietly, and nothing particularly impressive occurs. However, in the 22nd, 23rd, and even 24th centuries, it happens that nature decides to put on a real parade in the sky, as if specially prepared for spectators. And in this remarkable year of 2025, it seems intent on exceeding all expectations. It's as if the universe decided to stage a whole spectacle before our eyes, inviting numerous guests from space, purely to amaze us with its splendor and mysteries. Allow me to introduce the main participants of this unusual cosmic show, 7 comets, which have been named due to their special characteristics and places of appearance. These are comets named Pan-stars, Cygnus, Stereo, Atlas K first, Atlas G third, Lemon, and Neat. Each of them is like a traveler emerging from the distant, uncharted corners of our solar system, carrying tiny fragments of ice, dust, and rocks. Passing almost simultaneously over several months, they seem to gather as a group, as if these cosmic visitors have come together for this unexpected meeting that no one planned in advance. One can imagine such an intricate situation, as if 7 friends each suddenly arrive at their meeting on the same festive weekend, claiming they are unaware of each other's plans and did not coordinate with one another. Perhaps they happened to be gathered together by chance, or maybe there is some invisible, mysterious guidance behind them. But it is compelling to suggest that precisely in this short period of time, just a few months, all these comets seem to have been brought together by something common, which astronomers call the swarm effect. This effect, when many bodies, independently of each other, gather together as if following some internal script or rule, creating the impression that someone or something has specifically directed them here. The distribution of points in time, like random raindrops on a scorching pavement, creates a sense of chaos and unpredictability that is difficult to connect with something larger. But now try to imagine yourself in 2025, and certain patterns immediately catch the eye. 7 points gathered together in one area of the sky, as if someone accidentally dropped a handful of bright marbles, scattering them across the dark void of space. Such a pattern instantly attracts attention, arouses interest, and prompts questions about what is really happening. In most years, astronomers, both professionals and amateurs, spend months in intense work, hunting for the mysteries of space, for what is worth photographing and capturing. This year, observers have more than enough reasons for inspiration. The skies are dotted with images of numerous comet tails converging from different parts of the sky. These glowing long streaks trailing behind the comets, like trains, indicate the imminent approach of unfamiliar objects. Social media explodes with videos shot in slow-motion parallel, showing how some comets move synchronously, as if transforming into an incredible, coordinated celestial ballet, a single performance woven from myriad glowing trails. However, just when it seems that everything is clear and obvious, our investigation takes an unexpected turn. While these 7 comets move along their predictable orbits, and it is important to emphasize that this was indeed planned, one mystery still pulses in the darkness of interstellar spaces. Against the backdrop of familiar comets, an unusual feature emerges. This is the third confirmed interstellar object, designated as 301, ever discovered in our solar system. Unlike the commune of 7 comets, which, like a messenger guest from the depths of space, visited us for a short time, this object did not arise from local cosmogonic processes. It was formed around another star, in a distant exoplanetary system located beyond our familiar horizons. What is particularly striking is that this interstellar guest makes its only passage through our region, following a hyperbolic trajectory. That is, a very extreme and rapidly changing orbit, indicating its sudden intrusion into our bounds and subsequent departure. This moment is very precise, and it raises many questions that are uncomfortable for astronomers. Is such a purposeful visit caused by this coincidence? The most unusual year in the history of comet observations in our new era? Is it possible that all this is just an astonishing coincidence, a pure fluctuation of numbers and orbits? Or, on the contrary, is there reason to believe, and this is a more intriguing scenario, that there might be more complex, more deliberate intervention behind this? Throughout this research season, we will very precisely distinguish between facts and assumptions to avoid confusing the thought process and losing key evidence. When we talk about orbital data, observation log entries, precise measurements of brightness and trajectory, these are immovable, verifiable facts that can be trusted. These figures are our real foundation. At the same time, any hypotheses that go beyond confirmed science, and we will mark them specifically, are made solely as versions, assumptions, hypotheses that require further verification. It is important to emphasize that we do not intend to present rumors or unfounded guesses as evidence. Our approach is a strict adherence to the scientific method, where every consequence must leave an indisputable trace. And if there is even the slightest connection between this unusual year of comets and the interstellar object, then this connection must be visible, materially proven. But if we consider the possibility that some external influence, be it gravitational, electromagnetic, or something else that we have not yet been able to account for, pushed these objects to appear synchronously in our solar system, then we are faced with astonishing evidence of forces acting on scales that we can hardly fully comprehend. These forces may prove to be so powerful and unpredictable that they can fundamentally change our understanding of how objects move in space, how they interact with each other, and how their trajectories are formed. Imagine the implications of such discoveries: 7 comets unexpectedly arriving in the same area not by chance, but under the influence of invisible forces. In a system governed by known laws of physics, each orbit is a kind of historical chronicle. It contains traces of the forces that shaped its path. Each trajectory bears the imprints of processes and influences that acted on the object during its formation and movement. And if this is the case, these imprints should be detected on all these celestial bodies, raising the question, how do they manifest in their current form? An interstellar visitor, a special element of this mystery, adds a profound level of enigma yet to be unraveled. Triatlas, a large object carrying ice and dust formed in the fires of a distant star, enriched by cosmic radiation over millions of years of its journey through the vastness of space. Its chemical composition holds valuable information about how planets might have formed in other solar systems, making it a key element for scientists striving to understand the origin and development of celestial bodies beyond our own system. As it approaches our Sun, this giant luminary, the behavior of the interstellar object shows how the reaction of materials from other parts of the universe to stellar heat exchange can manifest in reality. But what if its appearance was not a coincidence at all? What if the same invisible force that could unite 7 comets, born in the depths of Earth or near it, directed this interstellar object precisely to our system at the most opportune moment? Such questions multiply and become more complex, forming entire fractal structures of thought. Fractals where each answer gives rise to new mysteries, new levels of understanding. A natural question arises. How can the presence of such an influence be detected? What mechanisms in space could act over such vast distances with such precision to coordinate the movements and appearance of objects, invisible and remote from each other? And if such mechanisms exist, what does this tell us about the nature of our cosmic environment, its structure, and the interactions that we do not yet fully comprehend? For now, we are set to closely study each participant of this unusual swarm of 7 comets, and remember, the universe rarely reveals its secrets without resistance. Every new discovery often begins with an observation that doesn't quite fit the existing model. It's the spark that pushes scientists towards new hypotheses and rethinking old assumptions. Every successful scientific breakthrough is initially accompanied by questions, wonder, and the feeling that we have finally come closer to the solution. But immediately, new complexities and mysteries arise, requiring further research and deep analysis. This situation resembles a scene where unknown guests approach us, bringing with them questions that can challenge everything we confidently believe to be true about the structure and functioning of our solar system. Until we fully acquaint ourselves with each of these 7 visitors, study their features and unique characteristics, we risk remaining on the path to understanding the essence, randomness, or something much deeper that connects them all. Evidence of their origin and influence is waiting for its time, and it's time to begin serious measurements, data collection, and observations. In this context, a new phase begins, the second part of our study, where we will compile a list of these participants to understand who they are. The observation period, during which we closely monitor the activity of celestial objects, begins at the end of March and continues until May 25th. This gives us several months to understand and track the approach of this mysterious object. What makes it particularly attractive to researchers is not only the possible brightness it can display but also its orbital geometry. The path of this comet comes so close to Earth's orbital plane that it becomes especially noticeable and easily observable from our latitudes. Such accessibility seems very convenient for astronomers and enthusiasts, as if it encourages observation and study. But the question arises, does this ease seem too convenient and even suspicious? Could it all be a coincidence, as it is believed to have likely wandered here from the distant and little explored corners of space, such as the Oort cloud surrounding our Sun on its periphery? While many objects move along their crusty orbits, interest in the Swan comet is a completely different story and deserves special attention. The story of its discovery is that a spacecraft called Solar Wind Anisotropus, designed to study interplanetary flows of solar particles, accidentally became an unsuspecting comet hunter. This happened thanks to its instruments tuned to detect hydrogen. They began to record the characteristic glow of cosmic bodies' atmospheres, similar to gentle sparking. In a short time, the Swan comets appeared in this device's data as if out of nowhere, like unusual bright spots flashing on the black screen of space. Moreover, their hydrogen emissions signaled the presence of the comet much earlier than our optical telescopes could photograph it. This hydrogen signature tells us a lot about the state of the Swan comet and its activity. Unlike silent stone objects that only glow when interacting with solar energy, this comet has already begun emitting gases, creating a characteristic hydrogen cloud, indicating its internal activity awakened by the Sun. Surprisingly, the comet remained active for several months, possibly even years, creating this hydrogen halo that clearly revealed its location and nature. For a comet hypothetically straying into the solar system, such seemingly calm behavior is very unusual. It appears remarkably prepared for its first appearance here, as if it had everything necessary for a debut, even though it may be traveling on an insanely long and convoluted orbit supposedly forgotten in the past. Perhaps a more dramatic discovery story involves the comet named Stereo. This spacecraft, designed to monitor solar activity and study solar wind and magnetic storms, suddenly detected a comet moving towards it in its peripheral field of view. Interestingly, this object was so close to our star that it became part of one of the most thrilling and simultaneously risky scenes in space. Stereotype comets are distinguished by their approaches to the Sun, often ending in dramatic events. Either their fragments disintegrate in a bright and spectacular explosion, or they undergo radical changes under the influence of high temperatures and solar radiation, transforming into unrecognizable shapes. Attention should also be paid to the timing of this phenomenon. The comet's arrival coincides with the period when solar activity reaches its peak, the so-called solar maximum. During these moments, the magnetic field of our star becomes particularly turbulent, as if thrown into tremors and whirlwinds. Many experts believe that this coincidence or even interconnection is not accidental, as this period creates conditions capable of attracting objects from outside, and thus understanding the causal relationship of such cometary journeys seems to emerge. As for the asteroid named Atlas G3, it occupies a special place among modern space object detection systems, as its origin and structure are closely linked to its earlier counterpart, the K1 system, which was also discovered as part of the same Hawaiian telescopic program. This program, one of the most advanced and effective in the world, makes an invaluable contribution to planetary defense, serving as a space early warning system. It regularly scans the entire sky visible from its observation points, passing over it every few nights, and in the process of this search, it detects any moving objects against the backdrop of bright star fields. It is this systematic and meticulous work that allows even the slightest movements of celestial bodies to be detected, which is the basis of its high efficiency. What cannot help but concern attentive and caring observers is the emerging trend they increasingly notice on the horizon: numerous recent discoveries of comets associated with the operations of Atlas systems. Not because the system itself somehow demonstrates weaknesses or shortcomings, on the contrary, it represents the pinnacle of modern technology for detecting asteroids and comets. However, when the same survey system begins to identify numerous members of an unusual cluster, the so-called swarm, the question arises: why are so many objects appearing, united by one group? What patterns might be hidden behind this? And yet it is the astronomical nature of these observations that compels scientists to seek explanations, connect individual discoveries, and ask questions. No less interesting is the comet named Layman. It introduces a special nuance into our cosmic collection, differing from familiar objects with its distinctiveness. An important participant in this matter is the Catalina Sky Survey Station, located on Mount Lemmon in Arizona, which has been systematically searching for near-Earth objects since the 90s. Over the years, it has accumulated one of the most comprehensive and authoritative databases covering small bodies of the solar system. The significance of the Layman discovery confirms the richness and accuracy of the data collected over the past 3 decades, as well as the long and painstaking process of determining its orbit. Although visually Layman could likely only be observed with binoculars, its position in our sequence of the swarm is precisely what makes it particularly interesting. It occupies an intermediate position within this cluster, neither coming to the forefront nor remaining in the shadows. Layman serves as a kind of link, filling the space between the members of this swarm, like a point carefully supporting the structure created with mathematical precision, which seems incredible in light of the ongoing events and patterns of orbital mechanics. It creates the impression that Layman is not just a random body, but a particle filled with historical ironic message, like a reminder of the importance of systematic observations. The program designed to track near-Earth objects, called NEO, ceased its operations back in 2007, yet the comets discovered during its active period continue to travel along their orbits, following a schedule calculated decades ago. These orbits, systematically refined based on thousands of observations from different stations and using various methods, show that there is no randomness in this process. A clear pattern emerges. All these objects were expected to arrive in our observation regions around the year 2025. There is no uncertainty, no surprises or ambiguities. Everything is so clearly and precisely calculated. However, this is where the main paradox lies. Among these comets, there is one accompanied by 6 satellites. Together, if their orbits are plotted on a single timeline, they form a well-coordinated and clearly defined cluster. This is not just a set of random objects discovered when they first became visible. It is a group of comets identified over different years using various methods. Consider a situation that at first glance seems like a simple statistical phenomenon, yet possesses deep meaning and requires special attention. The discovery of new comets in our solar system generally follows probabilistic patterns, resembling a random distribution over time. However, in this chaotic picture, there are sometimes periods when a cluster of objects appears, a short series of events consisting of 2 or 3 comets appearing within a few months of each other. Such a cluster, despite its modest intensity and limitation, represents a statistical anomaly that demands explanation. After all, 7 comets appearing over a relatively short period, each moving along orbits calculated with exceptionally high precision, these trajectories were formed millions of years ago. It was then, during the formation of the solar system, that these bodies began their long and continuous journey to the inner regions, and now we see them here, as if witnesses to ancient processes. Each of these 7 comets moves strictly according to the laws of gravitational mechanics, and there are no assumptions of randomness or improvised correlations in their trajectories. Their orbits have been precisely determined through observations and calculations performed with absolute precision, the result of modern technologies and scientific achievements. In this regard, there is no room for error, no margin for mistake or fantasy, since each trajectory was set millions of years ago when these countless tiny bodies began their multi-million-year journey through space to the inner regions of our system. And now, millions of years later, they unexpectedly find themselves on our orbital path, both close and at the same moment in time. The question that troubles every attentive observer and researcher is both simple and profound. What caused these completely diverse comets, moving in their individual orbits, to appear near our planet within such a narrow time frame? What force, acting over such vast distances and times, could have pushed these objects toward a synchronous approach? Obviously, we are not claiming that some organization or intentional coordination is behind this phenomenon. The only indisputable fact is that there is a pattern so evident that it cannot be ignored. This pattern prompts us to take a closer look, analyze, and understand the reasons for its emergence, as it seems worthy of special study and attention. Although each individual movement of a comet follows the completely natural laws of gravity and mechanics, their collective appearance in such precise synchrony raises questions that go beyond random coincidences. To properly assess the significance of this phenomenon, it is first necessary to understand how unusual it is under ordinary conditions to observe such a high level of comet clustering. Before drawing conclusions and seeking possible causes, it is worth studying what standard, typical years for our system look like, when only a few comets can be seen throughout the calendar year, if they can be seen at all. Moving on to the third part, it becomes clear, why can this clustering be considered abnormal? In a distant amateur or professional planetarium, ask about the likelihood of visible comets appearing in a year. Likely, an astronomer or specialist will sigh with relief and, after some analysis, tell you about only 1 or 2 objects that require a good telescope to notice. If lucky, among them might be that one comet, observation of which is possible even with binoculars, and which enthusiasts can track with enthusiasm. In reality, most years pass without the appearance of a single comet visible to the naked eye, adorning the night sky. This is the basic, familiar reality of observations, which includes patience, disappointment, and rare but pleasant moments when something unusual can be recorded. For the general public, comets have mostly remained ghosts, visible only in history textbooks and films about global catastrophes. They are perceived as a rare phenomenon. A survey telescope capable of capturing wide sections of the celestial sphere, as well as a rapid response system operating at the Haleakala Observatory located on the Hawaiian Islands, constantly scans all observable skies. These instruments regularly perform full or partial scans, allowing even the smallest changes in objects appearing against the backdrop of the starry sky to be detected. At the same time, the Catalina Survey, located in Arizona, conducts systematic and targeted observations of specific sections of the sky, meticulously and with high precision recording even the slightest movements and the appearance of new objects in particular areas. The recently launched Nearwise Space Infrared Observatory conducts observations in the far infrared range, detecting thermal signatures of various astronomical objects that would remain invisible or indistinguishable in the visible spectrum with ground-based instruments. These programs, throughout their years of operation, identify hundreds of new celestial bodies, comets, asteroids, and others, yet most of them, destined for immortality, remain unseen by our eyes and do not appear in surveys accessible to the general public. Only a tiny fraction, just a few objects from this multitude, achieve such brightness and size to become noticeable even to an untrained observer with limited capabilities. Statistical analysis shows that in any given year, there is a probability of discovering from 0 to, at most, one object that becomes bright enough to be seen without professional instruments. At the same time, it is estimated that 2 or 3 other objects may reach a brightness level that allows serious amateurs and enthusiasts to observe them without special technical equipment. However, despite the improvements in technical equipment and the expansion of search capabilities, this does not explain the anomalous and extraordinary phenomena observed in the year 2025. A meticulous analysis shows that although modern telescopes find slightly more objects overall, the percentage of those that turn into bright comets remains within historical models. That is, there is no unusual increase in the likelihood of their appearance. The improved sensitivity of instruments allows for the detection of objects far beyond previous capabilities, in dimmer and more distant areas. But this does not mean that the brightness of comets somehow increases, since the natural parameters affecting their luminosity remain the same. Courageously, it all comes down to their natural properties, size, composition, and distance from the solar luminary, which most influences brightness. These parameters were encoded millions of years ago, at a time when gravitational disturbances first shook them, sending particles on a perilous but inevitable trajectory toward the inner regions of the solar system. Modern surveys merely record what has already been predetermined by nature, and technological changes cannot affect natural laws. Simply put, our ability to see bright comets in the sky depends on their intrinsic characteristics and their position, size, chemical composition, and distance to the Sun during the closest approach. These characteristics were formed millions of years ago, under the influence of gravitational processes. It was then that their natural behavior and potential were established. All modern detections are rather just confirmations that such objects are approaching the inner regions of the system, not their creation or increase in brightness. In other words, we see more bright comets in the year 2025 not because surveys have suddenly become more sensitive or capable of detecting new objects, but because objects long prepared for a global phenomenon have simply arrived in our observation zone, which was an inevitable result of their natural development. This understanding is particularly important for interpreting what is happening. If the increase in the number of bright comets were explained by some clustering or concentration of objects, then such patterns should have manifested in other periods of the development of telescopic systems. Yet, despite this, against the backdrop of steady technological development, we observe 2025 as an exceptionally spacious and peculiar exception. Despite numerous uncertainties and challenges faced by modern comet observers, experience and intuition help them form a fairly reliable understanding of which celestial objects deserve special attention. When professional astronomers express surprise at the richness and packed schedule of events planned for 2025, their reactions often reflect their many years of observing faint, initially inconspicuous objects that gently, almost imperceptibly, flicker against the silent and boundless sky. These specialists are well aware of how difficult it can be to predict which events will captivate public attention or draw them to study. One of the factors complicating this year is the activity of our Sun, which adds a new degree of complexity to an already unusual astronomical calendar. Neither the northern nor southern hemisphere anticipates how significantly solar activity can fluctuate during the 11-year cycle that marks its cyclicity. During this time, solar phenomena undergo a series of calm periods, during which the star's surface is practically unadorned by sunspots and flares, and active phases, when the Sun exhibits fierce flares, coronal mass ejections, and powerful solar storms. For 2025, a period coinciding with the solar maximum has been recorded, a moment when the magnetic field of our star reaches the peak of its turbulence and restlessness. It is during this time that solar storms can significantly affect the outer parts of cometary objects, causing dramatic changes in the structure of their tails and creating impressive visual effects that one would not expect from faint and modestly bright comets. Solar active events contribute to comets within the inner solar system manifesting much brighter and more expressively than during periods of minimal solar activity. During solar maximums, when the solar wind fiercely attacks the interplanetary medium, comet tails expand and become more photogenic, providing astronomers with a unique opportunity to capture them with extraordinary clarity and detail. It is important to remember, however, that solar activity is not responsible for the mere presence of comets in the solar system. It only affects their appearance and observability. The objects we can see and study have already been set on their trajectories and encounters planned for the current year, regardless of how turbulent or calm solar activity may be. It would be incorrect to attribute the influence of solar flares and storms to why these 7 comets decided to reveal themselves to the world in 2025. Their appearance was predetermined by fate, dictated by physical laws and orbits established long ago. Of course, the solar maximum can significantly enhance their beauty and make observations more thrilling, but it does not explain why this particular year has become the time for such remarkable cosmic visitors. As we will see, there is a deeper reason related to the peculiarities of human psychology, which shapes our reactions and interpretations not based on objective astronomical factors. This is one of the complexities of such observations. Our internal perception often drastically distorts reality, leading us to believe in patterns where none exist. The human brain has been evolutionarily conditioned to recognize patterns even in random data, as it was crucial for our ancestors to quickly detect recurring scenarios for survival. In other words, the ability to see connections and patterns where there are none has become an important element of evolutionary development. This was necessary to promptly respond to potential threats or find resources. This trait of perception serves us well in everyday life, helping us navigate complex situations, anticipate developments, and recognize signs of danger or opportunity. However, at the same time, it creates a false sense that the human mind struggles to perceive these clusters of objects as a result of pure chance, especially when it comes to phenomena that resemble unusual patterns or synchronicities. In our research work, an important task is to distinguish truly objective anomalies, based on real statistical deviations, from those structures that may seem significant to our brains, as human perception tends to seek patterns even where there are none. Therefore, it is necessary to develop and implement measurable criteria to determine when the observed clustering of objects goes beyond ordinary fluctuations of a random nature and becomes a signal of hidden causes or mechanisms. In this context, a thorough orbital analysis proves to be an especially important tool, helping to understand the nature and origin of such clusters. If our 7 space objects, comets or other celestial bodies, harmoniously respond to subtle gravitational influences, may have common sources, or exhibit synchronized disturbances, exceeding expected patterns in terms of statistics, then it is logical to assume the presence of external coordination. Conversely, if these clusters are merely visible patterns arising randomly from vast datasets, such coincidence is the most reasonable explanation for the circumstances. Establishing the truth of such an assumption requires a high threshold of evidence. Reasonable hypotheses demand equally convincing and substantiated evidence. This is particularly true in cases involving unusual events related to the synchronous approach of 7 comets, as such a phenomenon in itself seems extremely non-trivial and requires careful verification. Such situations call for the emergence of so-called detection signatures, compelling signs confirming the truth of the hypothesis and capable of convincing skeptical astronomers and scientists who are accustomed to debunking false correlations or random coincidences. In preparing to investigate potential mechanisms of such unusual coordination, it is important to remember that the universe sometimes unexpectedly presents entirely unique surprises, challenging our notions of order and the nature of things. Sometimes the most improbable explanation turns out to be correct, and coincidences may conceal deeper, fundamental truths that require thorough and multifaceted investigation to uncover their true content. The important question is what force or mechanism is capable of coordinating objects over such vast distances and extended timescales. Could our interstellar visitors, such as comets or other bodies, be the missing link in this cosmic puzzle? The fourth part of our narrative is dedicated to the invisible hand, the hidden mechanism involved in mysterious patterns that at first glance seem inexplicable. When astronomers encounter inexplicable or unusual patterns, it is natural for them to turn to the two main forces governing the motion and behavior of objects in space: gravity and electromagnetism. These two forces excellently describe almost everything that happens in space, from the trajectories of planets and satellites to the behavior of charged particles in comet tails and the distribution of magnetic fields. It is through them that the movement of millions of objects is managed, and they are most likely to explain the observed phenomena and mysteries. If any means or mechanism truly directs 7 comets to synchronous arrivals, it is logical to consider their interaction precisely through these forces that govern cosmic processes. Let's start with gravity, as it is the unconditional and most stable master of choreography, controlling the movement of bodies within the solar system. Every mass-bearing body warps the fabric of space and time around it on an invisible level, creating a complex architecture, an internal force structure that determines the orbits of planets and the trajectories of comets. Gravity acts over infinite distances, and with mathematical precision, it allows astronomers to predict the most distant and complex celestial events decades, and sometimes centuries, in advance. Despite Jupiter's mass being only 1,000th of our native Sun's mass, it nonetheless possesses significant gravitational influence, allowing it to affect the orbits of asteroids and comets in our solar system. This influence is not limited to simple, insignificant seepages of force but manifests in such volume and character that its impact is easily recognized and calculated by specialists. For any object to push 7 comets simultaneously toward their coordinated approach to the Sun, its mass would need to be comparable to that of a large planet or even greater, because gravitational influence of such magnitude is a concentrated force requiring very significant energy resources and weight. We are not talking about quiet, accumulating over millions of years weak nudges that gradually alter trajectories, but about such sudden and powerful gravitational force that could leave clear and obvious traces in the orbital characteristics. Mathematics, strict and immovable in its laws, provides us with an undeniable mechanism for determining influences and their traces. All the orbital parameters of a comet, its inclinations, eccentricity, or time of passage through certain points, directly reflect the gravitational efforts it has been subjected to throughout its path through space. These unique signatures, these gravitational fingerprints, cannot be hidden or masked. They are unchanging evidence of the forces acting on the object. If any massive and hidden corporeal source were directing our 7 comets, its influence would inevitably leave traces in their orbital characteristics, making these traces clearly noticeable to observers and scientists. Jupiter has already demonstrated in practice how such a gravitational guiding force works. It has not only carved paths in the asteroid belt, creating so-called tracks along which many small bodies move in stationary orbital paths, but it has also captured an entire group of asteroids known as the Trojan asteroids, which follow its orbit and are held there by its gravitational force, creating stable families. Moreover, the energy of its gravity and interactions with surrounding bodies has led to the redirection of randomly moving comets, through random collisions and gravitational disturbances, into specific directions and orbital trajectories, highlighting Jupiter's role as a natural gravitational conductor. These effects can be measured with precision, the resulting forces calculated, and future interactions predicted with a high degree of certainty. It is through these observations and calculations that we have a powerful tool for identifying hidden or subtle guiding forces affecting objects in our system. If there were any unknown large object whose gravitational efforts influenced the position and movement of our cluster of 7 comets, we would have noticed clear deviations or synchronous changes in their orbits indicating a common cause. These gravitational disturbances, manifesting as unified signals in orbital dynamics or as large-scale gravitational patterns, could well serve as indicators of such a hidden source of influence. The absence of such evidence, that is, the lack of previously expected changes and deviations, equally argues against the hypothesis of gravitational coordination. In the absence of corresponding orbital signals and anomalies, it can be asserted with near certainty that no common gravitational director or organizer is at work in this case. As for electromagnetic influences, they too can have an effect, but they do so in a completely different manner and with less force. Comets, like any objects in space, accumulate electric charges as solar radiation ionizes their gas clouds, creating electric fields around them. These charged particles react. Moreover, electromagnetic phenomena on cosmic objects create unique and characteristic signatures in their spectra and the behavior of their tails, which under proper conditions could not be hidden or ignored. If powerful magnetic fields arising in the region of space somehow affected our 7 studied comets, any scientific observers using modern observatories would swiftly detect clear signs of this influence. This is why astronomy has certain criteria and standards for detection that help separate real physical effects from speculation and false assumptions. Genuine scientific research, whether in the area of gravitational or electromagnetic influences, must leave behind convincing, observable, and rigorously analyzed evidence. These include parameters such as common orbital elements indicating possible influence of certain factors on a group of objects, persistent or significantly exceeding measurement errors of perturbations, as well as synchronized anomalies that cannot be explained by the independent nature of each body's evolution. These signs help identify any potential indications of coordinated influence, if such exist, and distinguish them from random coincidences or statistical outliers. By applying such systematic evaluation criteria to our 7 comets, Pan-STARRS, Swan, Stereo, Atlas K Unit, Atlas G3, Lemon, and Need, we can attempt to determine whether their orbital characteristics show signs of a common external influence. Specifically, it is interesting to understand whether the trajectories of these objects are the result of forces beyond the traditional gravitational model of the solar system. In preliminary analysis, the answer is disappointing for conspiracy theorists, yet quite justified for those adhering to the classical physics concept. Each of the mentioned comets moves along its own independently formed orbit, which complies with known gravitational laws. The regions of their origin, the inclination of their orbits relative to the equinoxes, and the timing patterns of their appearance show no signs of systemic coordination beyond random statistical variations. In other words, the available data suggests that these objects evolved independently of each other, following the law of their unique trajectories created under the influence of familiar gravitational forces, the force of the Sun, as well as random encounters with planets and remnants of the solar system's ancient evolution. It is important to emphasize the absence of any signs of explicit synchrony or mutual correlations between the trajectories of these comets that would indicate a deliberately organized influence or hidden coordination from above. The objects may be at different points in their orbits, their nodes, the points of intersection of their trajectories, are far apart, and no subtle but measurably significant dependencies in their movements have been detected. Statistics show that this is simply a set of independent travelers, each departing from its original homes into interplanetary space, forming their independent paths under the influence of known forces, gravitational perturbations, random collisions, solar wind fluctuations, and other natural factors. Meanwhile, they reach their bright peak, and their activity reaches its apex, roughly within the same time interval, which is largely coincidental and not evidence of a common hidden guidance or external controlling mechanism. The orbital trajectories of these objects tell of diverse paths of origin and evolution, indicating a spread across different regions of the outer solar system. They originated from processes occurring in distant parts of the protoplanetary disk and were subsequently ejected from their original locations, moving along various routes shaped by predictable gravitational influences, coinciding only by chance at certain moments in time. If there were some hidden shepherd controlling or coordinating their appearance and movements, we might expect to detect subtle influences. Unlike the 7 classical and well-known comets that regularly visit our solar space, this interstellar visitor is fundamentally different. It does not adhere to the familiar gravitational laws governing objects within the orbit of our star system. Its hyperbolic trajectory is undoubtedly linked to an external origin, meaning its path extends beyond the boundaries of familiar cosmic thoroughfares, creating the impression of an alien body that has penetrated our cozy cosmic neighborhood from an unknown source, possibly with very unusual intentions. Such influence is difficult to explain with traditional physics, as it seems incredible and requires a rethinking of familiar perspectives, especially in the context of mechanisms that might affect the behavior and dynamics of comets, despite their minuscule mass and brief time within the solar system. Could this interstellar object, despite its modest mass, somehow influence the passage of time or the behavior of comets, which are typically considered very sensitive to gravitational fields? Could it somehow affect their orbits through mechanisms we know little or nothing about? These questions transcend ordinary concepts of the physical world, yet they are very relevant and demand careful consideration, especially in light of the unusual circumstances surrounding our interstellar guest. The obvious limitations associated with Triatlas acting as some observer or relay underscore its external origin. Its presumed mass is far less than planetary, making its gravitational influence barely noticeable and thus practically incomparable to the effects of large celestial bodies. The rapid passage of this object through our solar system leaves very little time for any significant disturbances in the orbits or behavior of comets to occur. Its trajectory also does not intersect closely with any of the 7 known comets, ruling out the likelihood of close encounters capable of causing measurable effects. However, despite these difficulties, the coincidence of the arrival time of such an object with a period of increased comet activity is very alarming for those who prefer the cosmic picture to remain as explainable as possible and free from inexplicable correlations. The arrival of the interstellar guest coincided with the most active year for comets in the past few decades, and this seems too convenient to be mere coincidence. Even if we assume that Triatlas is not capable of directly influencing the orbital parameters of comets, we cannot rule out the possibility that its presence is somehow related to conditions that create prerequisites for increased activity and the number of detectable objects. This issue opens up an exciting area for speculation among scientists because, although such evidence is absent, it raises interesting thoughts about possible connections, even if indirect. It should not be considered as involving some mysterious or exotic physics like invisible rays or violations of the basic laws of nature. Rather, we are wondering if the arrival of the interstellar object coincides with natural cosmic processes that regularly enhance comet activity or increase the likelihood of their detection during certain periods. Perhaps Triatlas acts more as a cosmic indicator, or, in other words, a kind of signal pointing to the conditions under which observing comets becomes much easier and faster. Maybe interstellar visitors prefer to visit our system precisely at times when external gravitational influences, caused by the movement of outer planets or the gravitational influence of other cosmic objects, create prerequisites for the activation of cometary paths, accelerating their journeys to sunlight. These assumptions need to be given serious scientific grounding, moving away from simple speculations and turning to deep analysis. Yet, such ideas allow us to understand how, albeit indirectly, it seems. The alarm we are raising now is not a piercing signal of impending disaster or inevitable doom, but rather a measured and thoughtful tone arising from scientific curiosity confronted with an uncertain, inexplicable pattern. One can imagine it as a cosmic smoke detector, faintly blinking in the dark, not as bright and insistent as a fire alarm siren, but still causing concern and a desire to understand what is happening. In our celestial neighbor, in the cosmic space next to us, something inexplicable and unusual is happening, a disruption of the usual notions of the calm movements of celestial bodies. And to respond correctly, it is necessary to conduct the most thorough and balanced research, study all the details, gather data, and only then make final conclusions. The year 2025 is approaching, and it promises a spectacle in the night sky that can captivate both amateur stargazers and professional scientists. This year is expected to be a true celebration, with several bright objects appearing simultaneously on the celestial stage, each developing magnificent, glowing tails. These tails are stunning in their beauty and dynamics, and their photogenic nature is such that it occurs perhaps once in several decades, a rare once-in-a-generation event. Social media, to its delight or dismay, will be filled with topics showcasing time lapses of these celestial visitors swiftly moving across starry fields. These moments frozen in time, captured with the precision of ballet, will immerse the viewer in a sense of harmony and choreography of the cosmos, where each movement seems precise and deliberate. Of course, this spectacle itself poses no threat to our planet. Comets are essentially very fragile and delicate objects, consisting of a loose aggregation of ice, dust, and organic materials barely held together by their own weak gravity. As they approach the warmth of the sun, these bodies transform into spectacular, mesmerizing displays, bright and memorable, sparking the imagination and evoking a sense of wonder among observers. Typically, we see them literally disintegrate, becoming almost ephemeral, losing material that cannot be recovered afterward. Even the closest approaches of such objects to our orbit, involving as many as 7 comets, remain at safe distances in astronomical terms. The nearest approach, for example, of a comet tentatively named HT, will occur far beyond the Moon's orbit, and no potential danger to Earth or other planets arises in this situation. These flybys are more like spectacular events without the risk of collision, rather than signs of an impending catastrophe. The true alarm comes from the pattern recognition mechanisms that evolution has embedded in the human brain to ensure survival. These systems allow us, instinctively, when several unusual phenomena occur simultaneously, to seek the causes that triggered them. We are accustomed to believing that the grouping of such events indicates something important and hidden, some pattern and connection, rather than mere coincidences. Such a response served our ancestors well in detecting threats in their surrounding nature. This is why, at the modern stage, people sometimes transfer these same instinctive reactions to space, interpreting occurrences on its vast scale. We see 7 comets in the night sky simultaneously and automatically assume there is some reason that could link them together. The question arises: who sent these bodies? What forces could have so precisely and organizedly coordinated their appearance? Why now, and why are they all gathering together at this moment? These questions become especially relevant when considering the presence in this context. The history of our world gradually unfolds in the form of a narrative to which we, humans, attach particular significance due to our collective drive to understand the meaning and purpose of the universe. However, this very universe seems to be arranged in a rather unusual way. It may appear random and unpredictable, like the result of a momentary collision of numerous random events. In such a situation, our fundamental rule of responsibility and rigor becomes especially important and decisive. Every significant statement or hypothesis must undergo thorough scrutiny for compliance with modern laws of physics and be supported by real observations. Speculative ideas are permissible and even encouraged within the framework of scientific inquiry, but they must be clearly identified as assumptions or hypotheses, and their adherence to strict standards of evidence must be ensured. The importance of the aesthetic appeal of theories does not justify the promotion of unfounded or unverified ideas as indisputable facts. Beauty and poeticism cannot serve as arguments in scientific reasoning. A constant reminder of the distinction between a spectacular display and objective causality is a necessary part of rational thinking. Despite the richness and beauty of cosmic phenomena, their dynamism, resistance to artificial control, impressive power, and even threatening mighty impact, their nature remains mostly unpredictable and not fully subject to our plans. The universe annually generates natural events that exceed all our aesthetic expectations and perceptions, and this occurs without the need to resort to any fantastic or exotic explanations. Imagine a situation where increased solar activity, expected in 2025, may significantly enhance the effect created by a bright comet parade in the sky. During the solar maximum, frequent coronal mass ejections and powerful streams of high-speed solar particles are observed, capable of fundamentally altering the behavior of comet tails and their manifestation. On days of particular solar storms and strong magnetic explosions, comet tails can stretch across several degrees of the sky, creating stunning visual displays. In such a situation, the disappearance or shutdown of observation-related equipment sometimes creates the illusion that comets have somehow shed parts or are being controlled on command. Such spectacular scenes leave a vivid impression on viewers and generate a multitude of striking photographs and videos, in which it seems that 7 cometary visitors are synchronously responding to external influences. And social media is filled with images and videos that seemingly capture the simultaneous movements of tails, flares, and other unusual phenomena, creating the impression of some internal or possibly external guidance or influence. The reality, of course, is less dramatic and more prosaic, yet no less interesting. Each of the comets responds independently to the same solar environment. Their similar reactions create an effect of synchronicity, which at first glance seems controlled by a centralized force, although in reality, it is simply the combined influence of heightened solar activity. This effect can be illustrated by an example, like 7 differently colored flags that flutter in the same direction during a storm, responding to the common impact of the wind, rather than being controlled by someone. And considering that all these events occur at the peak of the solar cycle, it adds another element for contemplation: why is unusual comet behavior noted during this period? The question arises: is there any connection between solar cycles and the rate at which comets begin their journey through the inner regions of the solar system? Could gravitational or electromagnetic influences of solar activity somehow affect the timing of their arrival? There are many speculative questions, and although they do not yet have definitive answers, they are all based on observed phenomena and their measurements. It is known that solar activity strictly follows well-documented cycles that correlate with various space weather effects, including magnetic storms and solar flares. When we embark on investigating various anomalies and mysterious phenomena in our solar system, it is crucial to adhere to certain principles and frameworks that help us stay on the right path and not get carried away by false hypotheses. These frameworks require constant vigilance to timely detect and avoid the so-called confirmation bias, the tendency to interpret ambiguous or random evidence in a way that confirms our preconceived hypotheses or preferred scenarios. It is important to remember that, upon discovering, for example, the unpredictable behavior of comet tails, we should not immediately lean towards assumptions of mysterious external coordination mechanisms or extraterrestrial forces. First and foremost, natural causes such as the influence of solar storms and their activity should be checked, rather than seeking non-obvious explanations that may open the door to fantasies or unfounded assumptions. When we encounter bright flares or special light phenomena, our first step should be directed towards studying their natural sources. It is necessary to analyze the composition of the comet, calculate the level of solar heating, and primarily consider familiar mechanisms based on known scientific data, rather than assuming external or mysterious triggers that are usually not confirmed by observations. Similarly, when orbital anomalies or unusual movements of astronomical objects occur, one should not rush into hypotheses about unknown influences or those that have not yet been identified, but first check the accuracy of measurements and rule out possible sources of errors or disturbances related to the technical aspects of observations. This disciplined and sober approach ensures that our conclusions and assumptions are based on real facts and reliable data, rather than illusions or fantasies. This rigorous methodology does not imply a rejection of curiosity or a limitation on the ability to propose hypotheses and make assumptions. On the contrary, it serves to keep our sense of mystery and interest in harmony with reality, so that we do not allow ourselves to be carried away by overly romanticized or unfounded theories, but remain objective and focused on factual observations. After all, the universe itself provides enough mysteries and complex phenomena that we do not need to invent additional mysteries that do not actually exist. Otherwise, we risk getting carried away by superficial or false hypotheses, losing the ability to see the true picture. Nevertheless, cases such as the merging of 7 comets into a single clustering node deserve close attention and thorough analysis. This is a rare, and often unique event on an astronomical scale, directly indicating the possibility of deep patterns or factors that warrant focused investigation. Such a concentration of objects occurs very rarely, and therefore it becomes a reason for conducting serious research to understand what might have triggered such clustering. In cases where our analysis does not reveal anything unusual and only finds manifestations of random coincidence, supplemented by the capabilities of modern survey and observation methods, Such a conclusion will be an important step in understanding the dynamics of movement and interaction of objects in our solar system. It will help refine our knowledge and reduce the likelihood of errors in future hypotheses. But if the analysis shows the presence of genuine connections exceeding randomness, for example, correlations between orbital trajectories, synchronization of time intervals, or complex interrelations in the behavior of objects are discovered, then such findings could be the key to recognizing new aspects of the solar system's functioning. In cases where we see signs of common influences or indications of synchronicity, this could radically change our current understanding of how the processes subordinate to it actually work. In this context, particular importance is given to the situation where, for the 8th consecutive year, the president becomes the 13th in order, adding an element of surprise and turning a statistical coincidence into a potential mystery worthy of thorough investigation. This year, the presence of 3 such astronomical objects or events is not a coincidence in itself but rather a vivid signal. While science carefully and cautiously studies our unusual guest, the interstellar traveler, it is important to remember that the deepest and most important discoveries often begin with simple and seemingly insignificant questions about unusual patterns that sometimes hide in the world around us. From time to time, the universe sends us a signal, and anyone who can listen and observe may notice important clues. Sometimes these hints appear as coincidences, random encounters, unusual features of an object, or unforeseen signs that were previously overlooked. Such situations often lead to major discoveries. When a sudden alarm signal from a cluster or another cosmic phenomenon arises, scientists respond not with panic but with the proven tools of scientific research. Their task is not to favor emotions or guesses but to conduct precise measurements and thorough analysis, which ultimately provide explanations. Questions are not resolved instantly. Answers take concrete form only after detailed studies and meticulous checks. But to obtain these answers, it is necessary first to understand our main suspect, the interstellar wanderer, whose arrival has sparked many questions and debates among scientists. Now it is about the third confirmed interstellar object, known as the Third Interstellar Cosmic Wanderer, or by the designation accepted in scientific circles, 3ATLS. This is the name of the other large object passing through our solar system, a cosmic traveler born of another star, now making a one-time hyperbolic pass through our region of space. Unlike all other objects we have studied and have information about, this exquisite guest is not an heir of its own system or native planets. It is not a local resident or satellite. It is, in every sense of the word, an alien. And in this case, it is crucial to emphasize because such differences are of great significance. Every cometary object in our solar family was formed as a result of gravitational interactions within our system. It emerged from the same primary materials from which planets, moons, and asteroids are built. That is, all these comets are children of our own system, born in the so-called local space. But 3ATLS is a special case. It appeared beyond our system, formed in another star system approximately 4.5 billion years ago, in a complex and distant part of space that we can only imagine today. Its composition includes ice and dust that condensed around another star, and this material was once part of another stellar birth, other processes that we still barely understand. Imagine receiving a message in a bottle floating to you across the sea. Only in our case, the bottle did not float across an ocean but traveled between star systems in interstellar space. Its journey likely spanned millions of years. Throughout this long period of cosmic history, the cosmic visitor drifted through the vacuum of airless interstellar space, constantly exposed to cosmic radiation. Over these millions of years, it accumulated chemical traces, small stamps, of its incredible journey, particles and molecules that could detail the path taken through the harsh and cold cosmos. Paradoxically, the most important thing for scientists is that this object, despite its mysterious nature, poses no threat to Earth. Its flyby trajectory is safe, as it moves along a hyperbolic orbit, which, unlike the orbits of planets or asteroids, does not indicate a potential collision with our planet. At the end of its journey, this cosmic traveler will not linger with us for long. It will simply pass by at high speed and, following its hyperbolic trajectory, will be ejected back into interstellar space, never to return. This early activity, arising in the context of an interstellar object, suggests either an unusual chemical composition, possibly containing supervolatile substances capable of rapidly evaporating even at low temperatures, or the presence of an internal heat source causing gas emissions independently of solar heating. Both hypotheses provide important clues about the conditions existing in the star system from which this ATLAS supposedly originated. Scientific studies that typically accompany any interstellar objects focus on their unique status. They are a direct opportunity to glimpse another planetary system without crossing its borders. Each spectroscopic analysis, study of chemical composition, as well as photometric monitoring of brightness changes and precise astrometric tracking of this object's trajectory, creates a rich database. From it, valuable insights can be gained into the star formation processes occurring beyond our system, a sort of cosmic trace left in interstellar space. Nevertheless, our documentary is dedicated to a completely different, more specific issue. We ask the question, could this interstellar guest somehow be connected to unusual phenomena? The timing of the appearance of this object and the observed swarm of 7 comets may merely be coincidental, yet the statistical probability of their coincidence is of significant interest. It is so noteworthy that it cannot simply be ignored or dismissed, especially because if there is any real connection between this interstellar object, designated as 3ETS, and the appearance of our 7 traditional comets, it will manifest in the form of specific observable signs. Such signs could include signatures that remain upon rigorous data analysis, for example, certain temporal correlations exceeding the expected probability of random coincidences, orbital relationships implying a connection, and anomalies in the behavior of objects that show signs of being influenced by a common factor rather than the independent evolution of each. If such signatures are absent, this would indirectly support the view that everything proposed here is merely a coincidence, nothing more. However, if we find clear correlations, it would open the door to profound reflections on forces and processes operating on scales beyond our current understanding and comprehension. Imagine the surprise of discovery if it is confirmed that the interstellar guest somehow influences the behavior of solar system objects. In such a case, it would require a re-evaluation of existing concepts of interaction mechanisms as proposed by modern physics. This could imply the existence of connections between star systems that go beyond the familiar gravitational forces, connections that we can currently only hypothesize based on indirect evidence. Even without invoking hypothetical exotic physics, the need to thoroughly study the possible temporal correlation between the appearance of 3ETS and our swarm of comets becomes increasingly apparent. After all, interstellar objects are extremely rare. According to current statistical data, their arrival occurs approximately once every decade. They likely arrive randomly, unrelated to internal events or activity in our solar system. But this year, in the most unusual period in many years, we are dealing with an interstellar object whose appearance coincided with the emergence of an entire swarm of comets, 7 in total. Attempting to assess the probability of this coincidence does not require complex calculations. It is clear that if we assume the arrival of the interstellar guest and the emergence of comets are independent events, their joint occurrence should be extremely rare. Especially if each event is so unusual and exceptional, their combination raises increasing suspicions of a possible connection, as the probability of such an exact coincidence approaches 0. This raises important questions about the nature and causes of such coincidences, as well as potential influences that may extend far beyond the simple mechanism of gravitational interaction. Of course, in scientific research, it is not uncommon to encounter situations where a correlation identified between objects does not necessarily indicate a causal relationship. In other words, the presence of a connection between two phenomena or indicators does not prove that one directly causes the other. Moreover, a discovered, suspicious, coincidence in time also does not serve as convincing evidence that there is any definitive connection between these events. This is why conducting detailed, systematic studies aimed at uncovering true causal relationships or patterns is of particular importance in scientific practice. If we consider our universe as a great source of clues and lessons, then every opportunity to understand the little-studied relationships between interstellar bodies and objects in our local area is of immense value to us. Whenever we observe space, it is important to be able to listen and heed, as these data, like a message, contain an important lesson. Specifically, when assessing the brightness of the three objects that make up the complex, which can be tentatively designated as 3ATL, it is necessary to approach their characteristics very carefully and manage expectations thoroughly. The inability to correctly interpret changes in brightness, especially in such observations, can lead to disappointment and incorrect conclusions. So far, despite the potential beauty and impressive external state of these objects, among which are massive and mysterious comets, this interstellar visitor is likely to remain a subject of telescopic observation throughout its passage through our region. That is, it will not become part of a long-term observational and research project, and its visual effect for a non-specialist observing casually may be minimal or even unnoticeable. But despite this, its scientific value is extremely high. It significantly surpasses mere aesthetic appeal, as it carries unique information about the conditions that existed in the distant star system from which it arrived. For specialists, professional and amateur astronomers from around the world, coordinating observations during this short period becomes an especially important task. By joining forces, they strive to gather as much valuable information as possible during the short time allotted to us, as we have only one opportunity to study this unique cosmic visitor. Every photon of light that passes by our telescopes contains information about the conditions and characteristics of distant star systems. And if the chance arises, it must be maximized, as we are unlikely to have another similar astronomical visit. The hyperbolic trajectory of this interstellar object completely rules out the possibility of its return and repeated visits to Earth or our orbits. This is our only opportunity to study it. Therefore, every fragment of data obtained, every measurement, is a priceless window opening new horizons of knowledge for us. Simultaneously, we have the chance to discover possible connections with other large objects, such as the one provisionally named the Swarm of 7 Comets. If there are any linking connections between them, such as coincidences in brightness changes, synchronized variations in the characteristics of their tails, or temporal correlations in changes, their discovery would be a significant achievement. For this, it is necessary to conduct very careful monitoring of all 8 objects, both the primary hyperbolic visitor and the Swarm of 7 Comets. Only through systematic and comprehensive observation can any subtle signals of interconnection be identified. It is possible that anomalies may appear, initially seeming random, but in fact indicating hidden connections. Such signs, even if barely noticeable, allow for important scientific discoveries, adding new chapters to our understanding of interstellar pathways and processes. However, along with this, there is the complexity of discerning what is a true, genuine correlation and what is the result of illusion or random coincidence. Our human brain is a complex instrument, evolved over time. The assertion that an interstellar visitor influences the dynamics of comets moving along our solar orbits undoubtedly falls into the category of highly unusual and deeply intriguing research hypotheses. Such a thesis requires morally and scientifically justified, substantial, and convincing evidence before it can be considered worthy of attention. Meanwhile, as scientists focus on studying the orbital characteristics and calculated predictions of the behavior of a specific object, the third, Atlas, it is important to remember that the stakes of this search are greater than mere curiosity. They concern fundamental understandings of the nature and structure of our planetary system. If it turns out that there are real, consistently manifesting connections between interstellar objects and the internal dynamics of the solar system, it will open a new page in understanding the architecture and interaction of stellar neighborhoods on scales that previously seemed unattainable for the human mind. Such a discovery could radically change current theoretical concepts, which suggest the universe functions as a collection of isolated systems. In reality, it may be more interconnected, more filled with subtle and complex relationships manifesting on scales beyond any of our intuitive perceptions. Or perhaps, all of this might just be the result of a rare statistical anomaly, a chance in a chain of random events where our analytical abilities are tested on their capacity to distinguish pattern from randomness. In any case, the ultimate answer lies in data analysis, and it is time to take a closer look at the potential interstellar stalker that we are still wondering about, rather than having discovered. This alien has arrived from distant realms, its path etched in the geometry of its trajectory. Therefore, now unfolds part 7 of this story, about the complex and enigmatic orbit. The trajectory of the third, Atlas, resembles a cosmic passport, a document containing the record of its journey, which began in interstellar space and ends there as well. Unlike the elliptical orbits on which planets and familiar comets travel, confidently circling the sun in endless loops, our visitor follows a hyperbolic trajectory, which, according to mathematical description, indicates a high speed sufficient to leave the gravitational field of our system forever. Imagine a projectile launched from the depths of space, rushing towards our star, making a sharp bend around it, like a deft turn, and then immediately speeding away into interstellar void. This journey occurs once, with no repeat visits or second chances for observation. And that is why scientists say that Atlas passes through our vicinity only once, and we can capture it literally in real time. The analysis of the orbital elements of this celestial guest reveals a fascinating picture of its origin and possible future paths. The object approaches the solar system from a direction roughly corresponding to the constellation Perseus, although in interstellar space there are no road signs indicating its specific starting point or lineage. Its hyperbolic speed, the speed it maintains even after leaving the sun's gravity, points to distant travels spanning hundreds of thousands of years, originating from star systems located beyond our galactic home. What makes this route particularly intriguing for researchers is its inclination relative to the plane of the elliptical orbit, the so-called ecliptic, the plane where the orbits of planets, their satellites, and interplanetary debris are located. The object moves at a moderate angle, not descending from above or from below, relative to this plane, but passing by it on an inclined trajectory. This geometric aspect is important for understanding the likelihood of its gravitational interaction with the orbits of planets and other objects within the solar system. Even insignificant in the distant galactic latitudes, thousands of light-years away from our solar system, resides a mysterious guest. This cosmic wanderer, skillfully and stealthily traversing our astronomical expanses, follows a path dictated by its hypothetical trajectory, minimally altering the characteristics of our system and its complex mechanisms. Its passage through our stellar region occurs at an inclination that distinguishes it from other interstellar objects. It remains in general proximity to the orbits of planets and comets for a considerable time, allowing it to stay consistently within distances far enough for its gravitational influence on local objects to remain quite weak. In other words, even though the interstellar guest is near our astronomical boundaries, promising potential interaction, the distances separating it remain astronomical units, vast and unreachable for the intense gravitational influence typical of close encounters. Nonetheless, this course of events does not rule out the possibility that this guest, moving at an inclination of 30 degrees relative to the plane of the ecliptic, spends months gliding along the same general region of spherical space. Meanwhile, in this area, other known comets, including 7 traditional objects, actively make their approaches to the Sun, covering the sky with their solar and interplanetary journeys every year and every month. Such simultaneous coexistence creates a complex geometric picture, further complicated by the fact that our interstellar guest moves in the opposite direction, contrary to the rotation of most objects in the solar system. This movement, opposite to the usual, leaves its mark on the mechanics of interaction, creating additional velocities and relative parameters that far exceed those typical of normal cosmic collisions and approaches. When an object moving at speeds exceeding the usual, along orbits revolving around the Sun, such as the interstellar guest, passes by, the relative speeds of it and surrounding objects increase significantly. At such moments, gravitational effects are minimal, as the fast-moving object spends much less time in zones where force fields distort trajectories or cause potential disturbances. In the event that an object similar to the 3 Atlases somehow influenced the orbits of local comets, which is considered unlikely, the reverse motion of the interstellar guest would actually reduce the strength of such interactions. It would act as a kind of natural filter, reducing the duration and intensity of possible encounters, even if they were potentially close. These features of orbital characteristics play a crucial role in attempts to understand whether an interstellar guest could somehow influence the dynamics of a group of 7 comets, each following its own individual trajectory. Any potential connection or influence should manifest not through close collisions or long-term gravitational effects but through mechanisms based on more subtle, possibly cartographic movements. In this understanding, the mere obsessive theory that an interstellar guest would simply drop by our regions and alter the trajectories of comets becomes increasingly unlikely. However, the geometry and positioning of orbital nodes, the points where the paths of the interstellar object intersect with the plane of the ecliptic, still leave room for hypotheses. These nodes represent specific moments in time when the distance between them and the comets reaches its minimum, and the probability of mutual influences increases. These intersection points, or nodes, ascending and descending, have strictly defined dates that can be calculated with high precision based on known astronomical data. If these dates coincide or align with periods when our group of 7 comets exhibits unusual light flares, anomalous tail movements, or unusual activity, the investigation focuses on identifying what can be considered a deviation from the usual behavior of these celestial bodies in conditions where their behavior is inherently characterized by significant fluctuations and unpredictability. Throughout their lifetime and when passing close to the Sun, comets display a variety of phenomena. Their brightness may change slightly, sometimes a bright tail appears, and even orbits, seemingly firmly established, shift or modify slightly. All this occurs because comets actively respond to solar heating and forces caused by outgassing, leading to the ejection of material particles that alter their behavioral characteristics. Under such conditions, proving the presence of any special activity or connection requires establishing a very high level of criteria to exclude manifestations typical of ordinary, regularly recurring processes in comets. Statistical analysis becomes an important tool, allowing for objective decisions on this matter. This requires continuous observation of all known 7 traditional comets and meticulous recording of every change in their brightness, the appearance of tails, or any other noticeable manifestations of activity. Subsequently, this data can be processed and analyzed to determine whether such events occur more frequently than by chance and whether they tend to happen around specific orbital dates or features of their passage through important cosmic points. The null hypothesis suggests that the combination of 3 comets, such as a trio, an atlas, and a swarm, in this case, 7 comets in total, are not related to each other. It asserts that all instances of unusual activity should be evenly distributed over time, showing no correlation with specific stages of their orbital movement or with moments associated with their approach to the solar body. If the study finds a significant deviation from this even distribution, it serves as a strong indication of a certain connection or interaction mechanism between the objects, even if the nature of this mechanism is not fully understood. Thus, any significant deviations from the scenario of random event occurrence may indicate either the presence of hidden connections or the influence of external factors affecting all comets simultaneously. At the same time, it is important to avoid systematic errors and the tendency to confirm one's hypotheses by ignoring cases where expected patterns do not manifest. A well-thought-out study involves recording all possible events that may be significant, not just those that seem to confirm assumptions about connection or interaction. In this context, the orbital evolution of a comet, such as the object named Triatlas, provides an additional data source for testing hypotheses about possible connections. As this object approaches perihelion, the closest point of its orbital passage around the Sun, solar heating is expected to increase activity and stimulate weathering, which in turn may trigger reactions in other objects. If there is any form of connection or coordination mechanism, such reactions in other comets should manifest precisely when the observed activity indicators of the Triatlas object reach their peak or go through key phases. The model predicted brightness curve of this object shows a gradual increase in brightness as it approaches the Sun, which is a typical scenario. Occasionally, this process may include sudden flares or outbursts, altering the behavior dynamics, arising from the rapid evaporation of volatile materials or fractures in internal structures under thermal stress. All these events are recorded at predicted times and at specific points along the orbital path, helping to identify patterns in their occurrence. If it is found that the considered group of 7 comets reacts to the activity of the Triatlas object, these reactions should occur with a certain temporal correlation, coinciding with the predicted time frames of flares or brightness jumps. The closer these reactions are in time to the predicted events, the more this theory, suggesting solar influence on the behavior of interstellar objects, is based on the idea that any manifestations of such influence should be linked to specific cosmic events. In particular, it is assumed that any changes in the behavior of comets or similar objects can be recorded at times when strong solar phenomena occur, solar flares, coronal mass ejections, or streams of high-speed particles that interact with their surrounding atmosphere and may appear measurable even at significant distances. If the solar trigger hypothesis is correct, the presence of such solar events will serve as clear evidence that all observed correlations are due to known mechanisms associated with the physics of solar activity. This will allow for the exclusion of hypotheses about unusual or exotic means of coordination, such as extraterrestrial origins or other extraordinary processes. Moreover, the orbital characteristics and spatial parameters of hypothetical visitors, such as the third cosmic object, as well as data analysis in the atlas, allow for a significant limitation of the time during which any impacts on objects within the solar system are possible. In the case of a hyperbolic trajectory, characterizing a fast-moving incoming object, such an encounter, or more precisely, its flyby, will be very short in duration. On average, such an event may last only about 18 months from the moment of its initial detection until it leaves the observable area, coming within our astronomical visibility during this time. Such a time-limited interaction makes it unlikely to detect very weak effects that could accumulate over centuries or even millennia. That is, any minor changes occurring during a short-term visit are unlikely to become noticeable using modern instruments, as their impact would be too insignificant to manifest against the backdrop of very weak or long-term changes. When we analyze the forecast of perihelion passage, that is, the moment when the object reaches its minimum distance to the Sun, it is important to remember that orbital mechanics operates with precision to the finest details. Regardless of hypotheses about unusual or exotic mechanisms that might influence the behavior of this object, its path is determined by gravitational forces, completely indifferent to human assumptions about extraterrestrial coordination or interstellar influences. All indicators, numerical data, and geometric parameters speak for themselves. History unfolds through meticulously measurable parameters, and the connection between the trajectory and the current state of the object is confirmed by facts. And yet, the question of whether this history is connected to our specific swarm of 7 comets or if it is merely a coincidence remains open and requires further study. The most likely answer will come at the moment of perihelion. At this point, when the object approaches the Sun at its closest distance, many mysteries may be resolved. Part 8. What exactly happens at the moment of perihelion? This stage represents a kind of point of no return and a potential point of truth for any comet. It is the moment when many months or years of gradual approach suddenly turn into a flurry of activity, and the object's speed sharply increases, reaching its peak. For the third Atlas comet, this moment is of particular importance because it is during this period that it experiences the maximum intensity of solar radiation and solar wind streams, leading to significant changes in its external appearance and internal state. The physics of this process is both predictable and dramatic. As the comet approaches the Sun, its brightness increases according to the inverse square law. The closer it gets, the stronger its light and heat emission become. At a distance less than half of the original, already existing distance, the icy components, which have remained in a state of rest and frozen solidity all this time, begin to evaporate intensively. As a result, a gaseous envelope appears, the comet's tail and gas stream, transforming the previously dark and barren object. These discrepancies in chemical composition should manifest during spectroscopic analysis precisely when the comet passes perihelion, the closest stage of its orbit to the Sun. Each molecular species in its composition, upon evaporation and excitation by solar rays, creates characteristic emission lines in the spectrum. Thus, the spectrum recorded from the three interstellar objects will essentially serve as a unique chemical fingerprint of the environment in which they formed, preserved over millions of years of interstellar travel. If the study confirms the existence of genuine connections between the Triatlas comet and the swarm, consisting of 7 separate objects, the moment of perihelion will provide the most likely window for discovering new and possibly unexpected facts. The intense heating from the sun's rays, causing peak comet activity, may also activate mechanisms capable of coordinating the behavior of many objects simultaneously. Scientists should pay attention to signs that manifest both overtly and covertly, as both can carry important information. For example, a sudden increase in brightness usually indicates the onset of intense evaporation, especially of volatile substances or freshly exposed icy areas that were previously protected by a dense dust crust. Such outbursts can increase the brightness of a comet tenfold or more in just a few hours, creating unique observation opportunities and providing insights into its internal structure and composition. It should also be considered that jets of material emanating from specific areas of the Triatlas nucleus may create slightly asymmetric thrust effects, influencing the comet's trajectory. These non-gravitational forces have long been known in the case of traditional comets, and their detection in interstellar objects will provide unprecedented information. They will show how materials borrowed from other star systems react to the influence of the Sun's gravitational and magnetic fields. The development of the Triatlas tail is particularly important for research because it serves as a living reflection of the processes of interaction between interstellar matter and the solar wind streams. Ion tails form when solar ultraviolet radiation ionizes the comet's gases, creating charged particles that move away from the Sun. Their movement is governed by the solar magnetic field, allowing scientists to observe how interstellar gases react to solar influences. The length, shape, and orientation of this tail, as well as its response to changes in the solar wind, will show how materials from another star system interact with the stream of particles emanating from our star. Any anomalous characteristics compared to typical comet tails indicate possible differences in the chemical composition or physical properties of interstellar materials, which in turn confirms their extrastellar origin. Dust tails, unlike ion tails, are governed by different physics. They are formed by radiation pressure and the flow of sunlight, rather than the magnetic field. The size spectrum of the particles they consist of, as well as their chemical composition, determine the degree of deviation from ballistic trajectories under the influence of solar radiation. Larger particles, having greater mass, partly deviate from their initial lines of motion, while the smallest grains, which can be only a few microns in size, under the influence of radiation pressure, form wide, curved tails, sometimes stretching several degrees across the sky. If the Triatlas comet forms an unusually long and dust-rich tail, it may indicate a composition rich in fine particles, which are highly sensitive to solar radiation pressure. Such an indicator will be an important argument in assessing its origin and physical properties, opening new horizons for understanding the characteristics of interstellar materials moving through our solar system. As it passes through perihelion, the comet may encounter a phenomenon known as fragmentation, an event in which part of the internal structure of this cosmic object suddenly breaks into many separate fragments. One of the most dramatic scenarios incompatible with the stability of a comet is precisely when, as a result of the influence of various forces within the comet, it breaks apart. These forces include solar heating, which causes intense warming of the outer layers, rotational stresses arising from the object's spin, and internal pressure caused by the evaporation of volatile substances hidden inside. Sometimes these forces are so weak against the gravitational binding within the comet that its fragile structure can no longer withstand and disintegrates, splitting into many separate pieces. These parts, detaching from the main body, move along their orbital trajectory, sometimes flying close to each other, creating a complex dynamic picture. In the case of the comet designated as Triatlas, the effect of fragmentation can be particularly significant. Why? Because it is under such conditions that access to the object's internal materials occurs. Those that have remained virtually unchanged since its formation in another star system. These usually hidden internal layers, exposed due to the breakup, offer unique opportunities for spectroscopic analysis, allowing scientists to study materials created in the early epochs of interstellar spaces without subsequent alterations. However, such disruptions also create challenges in research work. When many fragments move along slightly different paths, it becomes harder for scientists to track the integrity of the associated object. Visually, there is an illusion of coordinated behavior of the entire group of fragments, although in reality, their movements may be independent. It is so easy to confuse the manifestation of random effects caused by the complex geometry of trajectory intersections with actual coordinated connections between these parts. Against this backdrop, the situation is further complicated by the impact of solar conditions, especially when the comet designated as 3Atlas passes through perihelion, the closest point to the Sun in its orbit. During this phase, the solar environment changes significantly. The density of solar particles increases, magnetic fields intensify, and the number and intensity of coronal mass ejections rise. All this creates an extremely dynamic and variable environment around the comet, significantly affecting its external manifestations, especially the formation and behavior of tails. Under such conditions, space weather phenomena manifest vividly and can create quite impressive visual scenes. Tail breakups, separation of plasma streams, appearances and disappearances of structures, and the emergence of magnetic reconnection effects. All this results in comet tails, seemingly stable elements of space, appearing twisted, bent, or even shattered. These active processes occur independently within each individual comet, yet they respond to the same solar influences, creating seemingly coordinated effects that do not actually exist. The distinction between the real collective reaction of a cosmic object and the illusion of its presence lies in precise timing measurements and geometric analysis of the occurring processes. It is important to consider that the solar wind, a stream of charged particles, spreads from the Sun at a predictable speed, reaching different objects in orbit at strictly calculated moments in time. If the unusual behavior of a group of 7 comets, their divergences, accelerations, changes in orientation, coincides with events occurring within the inner sphere of solar activity, and cannot be explained by the delay in the spread of the solar wind, then such a correlation takes on special significance and becomes a subject of serious interest for scientists. Currently, numerous observational campaigns are actively prepared worldwide to monitor Comet 3ATC during its perihelion passage. Modern coordination of astronomical observations encompasses not only major scientific laboratories and professional observatories but also includes a wide range of specialized search systems and methods, such as space telescopes located beyond Earth's atmosphere, as well as ground-based observatories equipped with the most advanced instruments. All these means collectively create a unique opportunity for conducting the most comprehensive and detailed studies of interstellar objects, those rare cosmic newcomers that have ever entered our solar system region and attracted the attention of scientists. Each photon of light recorded during such observations represents an invaluable source of scientific data, revealing the properties and conditions of existence in another, distant star system. These data help to understand what physical processes occur there, what material components are present, and how interstellar bodies behave against the backdrop of different conditions. However, to achieve a full understanding, it is necessary to simultaneously monitor the entire configuration of the known 7 classical comets within the field of view during the same period. Such a multifaceted monitoring allows for the identification of possible anomalies in their behavior, which may not be random but related to external events or interconnections, for example, with the activity of the interstellar object known as 3IATLC. This comparative research method helps to distinguish simple, fully explainable comet variability from possible significant connections indicating deep interactions that exceed ordinary statistical expectations. In other words, it serves as a tool for detecting themes that go beyond the usual manifestations of celestial bodies: subtle, barely noticeable changes in brightness, slight deviations in tail shapes, or minor orbital perturbations. All of these may be the only evidence of mysterious and exotic physical interactions occurring under specific conditions, hidden from the view of ordinary methods. As we approach the next perihelion or passage, it is important to remember that despite the initial enthusiasm and rush to learn something new, the universe operates strictly according to fundamental physical laws that remain unchanged regardless of our expectations and hypotheses. Object 3Triatlas, as it glows and evolves while approaching the Sun, becomes brighter, its tails grow, and may even fragment. All of this depends not on predetermined scenarios, but on the object's intrinsic properties and its reaction to solar heating, a process that forces the interstellar visitor to change its appearance. These changes are observed not within specially designed programs or plans for delivering impressive news, but are essentially natural results of the object's interaction with the solar environment. The internal physical processes in the interstellar guest hold the potential for discovering new knowledge about the nature of interstellar materials, their behavior, and characteristics under solar activity conditions. At this moment, the question remains open whether the discoveries made during observations indicate a possible connection or interaction with the 7 comets in our group, and only careful and systematic observation can provide the answer. The cosmic clock ticks continuously and precisely, paying no heed to opinions or speculations, and most importantly, constantly provides the data necessary to distinguish genuine scientific discoveries from random coincidences or superficial conjectures. Part 9. The group of 7 comets and the role of the Sun. Our central star, the Sun, undergoes complex cyclical changes that far exceed the scale of human perception of time. These cycles alternate periods of relative calm with phases of significant activity, during which turbulent processes occur, unimaginable to ordinary perception. The 11-year solar cycle, the most well-known and important, governs this rhythm, reaching its peak in the 25th year, transforming the star into a brighter, more variable, and more spectacular version of its usual state. During the solar maximum, the high density of solar particles and intensified magnetic fields characteristic of this period can significantly enhance and extend the observable effect of comet tails, making them truly impressive and sometimes even astonishing, unlike the calmer solar periods when solar activity is less vivid and does not cause such intense changes. In this context, it is especially important to consider the phenomenon of coronal mass ejection, which represents a massive cloud of magnetized plasma ejected from the star into space with the force equivalent to 1 billion tons of material. Such a powerful event interacts with the delicate and vulnerable ion tail of a comet. When powerful magnetic waves and field distortions spread through space, they can impact the comet's tail, resulting in compression, twisting, or even complete detachment of part of the tail. These processes occur within hours and often produce some of the most spectacular and dramatic photographs of comets, where their tails appear unusual and even fantastical. Such tail-disrupting events occur precisely when the solar magnetic field, carried by the solar wind, abruptly changes its polarity. The resulting magnetic changes cannot always be quickly compensated by the current structure of the tail, leading to the old tail being detached and carried away into space as debris, while a new one forms under the influence of the adjusted magnetic environment. For those observing from afar without knowledge of space weather physics, such sudden and vivid changes may seem almost supernatural. In reality, the comet's tail at this moment may suddenly take on bends, knots, or spiral structures, as if defying the simple laws of gas or plasma physics, disappearing or evolving very quickly. In some cases, it may seem as if the tail is completely severed, creating the illusion of an attack or damage from external forces. However, in truth, these phenomena are a normal reaction of the comet to the extreme conditions of solar activity. The comet's body itself remains almost motionless and unharmed, staying safe, as only its thin ionized envelope, the tail, reacts to the changing magnetic environment. Visually, these changes can be so impressive that observers often begin to seek unusual or even fantastical explanations, instead of perceiving such events as the natural result of solar forces acting in space. This influence of the Sun becomes especially important for understanding the processes occurring within our study, as all 8 objects participate under the same space weather conditions. Our group includes 7 classical comets, as well as the hypothetical comet Triatlas, all of which are situated in the same magnetic and solar zone environment, subject to the same streams of coronal ejections, high-energy particle flows, and magnetic field variations characteristic of the peak solar activity. If all these comets suddenly exhibit similar and dramatic changes in their tails simultaneously, the most logical explanation is a reaction to common solar triggers. In such a case, there is no need to seek a mysterious connection or coherence between the objects themselves. Everything that happens is explained by massive solar storms and powerful emissions that affect the entire inner solar system almost simultaneously. The enhanced solar activity expected in the 12th year promises to be particularly intense and, accordingly, impacts the Earth's magnetosphere. These solar disturbances, caused by powerful streams of solar particles, can trigger geomagnetic storms that may disrupt satellite operations, interfere with GPS and navigation systems, and in extreme cases, even threaten power grids, causing outages in major cities and regions. Thus, the influence of solar activity in the 12th year is not limited to cosmic phenomena. It actively affects our earthly home, increasing social changes in the behavior of Earth's magnetic fields, and the resulting light phenomena known as auroras occur under the influence of solar storms, which often cause a shift in the zones of aurora occurrence to lower latitudes. As a result of this shift, those living in temperate latitudes sometimes have the unique opportunity to observe this bright and mysterious light spectacle, usually accessible only to polar regions. Such an amazing phenomenon, the result of enhanced solar activity, creates the impression of an almost supernatural spectacle, as its intensity and duration often astonish observers and make it an unforgettable event for astronomy and sky enthusiasts. However, it is important to distinguish the causes of such phenomena and understand that while the connections between different phenomena seem obvious, their nature requires deeper analysis. In particular, it is necessary to differentiate between causal relationships and coincidences, as solar storms influence both comet tails and Earth's magnetosphere, but this does not mean that comets cause these magnetic disturbances or cosmic activity. In reality, the Sun governs both of these processes independently, creating coincidences in time that do not indicate a direct causal link. This approach is especially important when it comes to interpreting the connection between the so-called 350-year solar activity cycle and various earthly phenomena, including satellite system failures, power outages, or anomalies in comet behavior. At such times, solar activity seems a more convincing explanation than assumptions that a tiny, distant comet could somehow cause such large-scale and sudden changes on Earth. The timing of the solar peak, or solar activity maximum, noticeably coincides with periods when unusual behavioral patterns appear in comets, whose fate remains a mystery to scientists. This fact raises a number of questions about possible connections between solar activity cycles and the frequency of appearance or arrival of comets in our inner solar system. Could the exertions of the solar magnetic field, streams of solar wind, or gravitational effects associated with the solar maximum influence the dynamics of cometary paths? Indeed, these questions fall more into the realm of hypotheses and conjectures, as definitive answers require thorough analysis and confirmation. It is desirable to consider statistical data over several solar cycles to determine if there is a pattern. Do periods of high solar activity coincide with an increase in the number of new comets or their earlier appearance than would be expected by chance? Such studies require careful separation of solar effects from potentially less discernible influences related to real or imagined connections between the 350-year cycle and a group of 7 notable comets, whose appearance intrigues astronomers and space enthusiasts. In the event of unusual comet tail behavior, the first step should be to refer to space weather systems specialized in detecting coronal mass ejections, high-speed solar wind streams, and other known solar disturbances. Professional space weather monitoring systems, which provide accurate and timely information about such events, will allow for the prompt correlation of solar flares and activity with comet behavior. Only after proving the absence of a connection with solar influences can more exotic hypotheses and conjectures be considered. Such a systematic, methodical approach helps avoid premature and unfounded conclusions based on the desire to find an unusual explanation at the expense of common sense. Reliable systems providing constant monitoring of solar activity and conditions in interplanetary space include heliophysical observatories, solar dynamics observatories, and ground-based magnetometer networks, which collect data on solar emissions, magnetic disturbances, and solar wind streams in real time. These modern tools allow astronomers and scientists to track changes in solar conditions and conduct analytical work on the modern space environment observation system, offering us unique and virtually unlimited opportunities to analyze comet behavior and identify various influences on their dynamics. Thanks to this infrastructure, we can not only distinguish phenomena caused by solar activity but also detect truly unusual and anomalous events that may indicate the presence of other influences not directly related to the Sun. For instance, if we imagine that solar activity reaches a very high level, the effect of its influence on the behavior of ordinary comets should generally be noticeable enough to stand out against the background of the overall level of solar fluctuations present in nature. Therefore, such influences, if they exist, should be detectable even against the backdrop of constant solar variability, which observers have been recording and studying for many years. The monitoring systems also play a crucial role in the amateur community, non-professional observers who provide valuable data that complement professional observatories and space weather systems. Photographers around the world, who monitor comets daily, make a significant contribution to scientific progress by documenting the behavior of their tails, changes in brightness, and structural transformations that often occur over very short time intervals. Often, this temporal resolution significantly surpasses the capabilities of modern professional observatories, making the data collection particularly valuable. A dispersed network of such observers ensures continuous and comprehensive coverage of observations across the entire spectrum of comets, constantly replenishing databases necessary for in-depth analysis. This information allows for complex correlation studies, comparing the dynamics of solar activity with the behavior of comets under various conditions. The more detailed and richer our dataset, the more confidently we can identify truly unusual phenomena and events deserving further, deeper study. The upcoming year 2025, when a new surge in solar activity is expected, is guaranteed to create conditions for active work across the entire research system. During such periods, solar activity reaches its peak, contributing to the frequent occurrence of various space weather events. This intense solar environment simultaneously offers numerous opportunities for capturing spectacular photographs of comets and their tails, while also significantly complicating the task of detecting subtle and weakly expressed effects that may manifest independently of obvious solar triggers. One of the main challenges in data analysis is maintaining strict standards of confirmation to ensure that the evidence is truly reliable and convincing. At the same time, it is necessary to remain as open as possible to the detection of genuine anomalies, as such unusual manifestations may reveal new, previously unknown aspects of the behavior of these amazing cosmic objects. The universe has repeatedly shown that often the most subtle connections and effects, initially perceived as impossible or improbable, ultimately turn out to be reality. During peak solar activity, special energetic conditions are created that can stimulate the detection of weak interaction effects that previously seemed unattainable for observation. At this time, as our research focuses on studying the impact of space weather on Earth's conditions, it is important to remember that solar activity plays a key role in shaping many dramatic and significant phenomena associated with the appearance of comets and their behavior near Earth. The question of whether solar activity affects comet behavior has long been resolved. It is a well-established fact. The question is whether the influence of solar conditions is realized in combination with other, more subtle effects that modern science has not yet fully explained or predicted. The cosmic dance continues, and its choreography is created by magnetic fields and streams of charged particles connecting our star with all the bodies in its gravitational sphere. However, within this familiar and seemingly well-studied picture, there may be new steps that have yet to be discovered and understood. In this complex and constantly evolving system, unexpected discoveries, new levels of interaction, and effects are possible. Part 10 of this study is called, Echo on Earth. The influence of space weather on our planet is a complex and intricate network. Geomagnetic storms are cosmic phenomena capable of causing significant changes in Earth's magnetosphere due to the impact of solar particles. When these particles, which are part of the solar wind, collide with our planet's magnetic field, they can induce electric currents in Earth's power lines. These currents, moving through circuits, can overload transformers and otherwise strain energy systems, sometimes causing them to overheat or even break down. Such situations create the risk of cascading power outages, where failures in one area escalate into widespread blackouts across the network, leaving millions of people without light and heat. A particularly striking example of such a danger was the storm of March 1989, which led to a catastrophic collapse of the power system in the Quebec region. This case vividly demonstrated how space weather, often perceived as a distant and inaccessible concept, can have extremely terrestrial, tangible consequences for the infrastructure and well-being of millions of people. It is worth noting that satellite systems in space are even more directly at risk. High-energy protons and electrons accelerated by solar storms easily penetrate the protective screens of spacecraft. As a result, both short-term disruptions and long-term damage to the sensitive electronics that control navigation, communication, and meteorological observations are possible. During periods of high solar activity, global positioning systems, satellite communications, and weather monitoring systems become significantly less reliable, as intense solar emissions interfere with data accuracy and equipment functionality. This fact is particularly critical for aviation, as flights at high altitudes and especially over polar regions are at increased risk. The Earth's magnetic field provides less protection from cosmic radiation there, increasing the danger of radiation exposure for passengers and crew, as well as the threat to onboard electronics. Consequently, airlines regularly take measures. They alter routes to avoid areas with heightened radiation levels and limit flights during periods of strong geomagnetic storms, striving to protect their passengers and equipment from the hazardous effects of space weather while simultaneously reducing the risk of emergencies in the air. All these consequences create a rather alarming and tense psychological atmosphere, fostering a desire to find rational explanations for the connections between celestial events and problems arising on Earth. It often seems that the coincidence of peaks in solar activity and the activity of comets or other cosmic objects is not a mere chance but evidence of an extraordinary connection. When comet activity reaches its peak simultaneously with the solar maximum, a period of intense solar activity, many experience the feeling that the timing and events align perfectly, giving them a special, even magical significance. Thus, power outages, communication system failures, and navigation issues begin to be perceived not just as consequences of technical malfunctions but as signs of a mysterious and powerful influence emanating from space, especially in situations related to this rare cluster of 7 comets. However, in reality, the mechanisms by which solar storms and comet activity affect Earth systems are entirely different. The reality is that solar storms impact technological infrastructures through well-studied physical processes, the interaction of solar particles with the magnetosphere and the ionized layer of the atmosphere. These processes occur independently of comets. Comets respond to altered cosmic conditions, increased particle density and magnetic field variations, since these celestial bodies, moving in the far reaches of the solar system, encounter unfamiliar streams of energy and magnetic fields. In turn, Earth's infrastructure reacts to the same streams or particles when they interact with the planet's magnetosphere, causing electromagnetic disturbances. Therefore, the connection between these phenomena is due to a common solar source, rather than any other factor. Modern systems for monitoring and warning about space weather operate with the same urgency and responsibility as mechanisms designed to track terrestrial natural disasters and extreme natural events. These systems allow for detailed correlation of recorded events related to changes in the space environment with possible disruptions or malfunctions in Earth's technical infrastructure. The link between sudden damages and technological issues with comet activity is particularly important, often sparking genuine interest and suspicion among specialists. In cases where disruptions in communication systems, power supply, or other critical technological facilities occur simultaneously with recorded geomagnetic storms, the likelihood that solar activity is the cause significantly increases compared to the possibility of comet influence, which is often considered a less likely factor. These assumptions are especially relevant in the context of increased solar activity expected in the year 2025, when the solar maximum promises to be particularly intense and prolonged. During such maximum periods, the probability of coinciding various phenomena and events increases to the point where numerous opportunities for correlation analysis arise. During these times, geomagnetic storms occur several times a month, creating constant conditions for random coincidences between space weather observations and technical problems arising in infrastructure. Often, these coincidences are the result of purely statistical patterns, which should not be attributed significant meaning or causal connection, as they may occur randomly without any real influence. An important source of information and an additional resource for monitoring are amateur radio operators, who have the unique ability to detect the effects of space weather long before official warnings are issued. Their networks, based on receiving radio signals and analyzing variations, allow for the identification of changes in Earth's ionosphere related to geomagnetic storms before these phenomena reach their peak. During periods of active solar flares, radio waves through the ionosphere begin to behave differently. Communication disruptions occur, as well as unusual patterns of radio signal propagation, which experienced operators can instantly recognize as signs of impending or ongoing geomagnetic events. This distributed network of sensors and specialists operates in a mode of constant information exchange, providing timely feedback on the state of space weather, allowing scientists and engineers to distinguish true solar impacts from potentially anomalous phenomena not related to this source. If, however, the three atlases are different, that is, influencing the Earth's electromagnetic field in some way, their effects should be detected using several independent monitoring systems set up to confirm such changes. In the research process, it is important to constantly monitor errors that arise in attributing the causes of events when several dramatic changes occur simultaneously, and there is a temptation to explain them with causes related to cosmic activity or random coincidences. Human psychology is strongly inclined to seek causal relationships between temporal correlations, especially when the time intervals between events seem meaningful and purposefully connected. The more unusual the individual phenomena, the stronger the hypothesis of their interconnection seems. However, statistics show that such clusters of events often occur quite randomly as a result of probabilistic processes. By flipping a coin long enough, one can see numerous sequences that seem incredible but are actually a natural manifestation of mathematical probability. A similar principle can be applied to observations of correlations between comet activity, solar weather, and disruptions in technological infrastructure. The main challenge lies in developing objective criteria to distinguish significant connections from random clusters of events arising from the complexity and nonlinearity of systems. For this, it is necessary to establish statistically expected levels of coincidences between different types of phenomena and to compare observed data with theoretical models and forecasts. In scientific circles specializing in space weather research, complex modern statistical technologies have already been developed. These technologies allow for intensive and comprehensive analysis of the relationships between different classes of events, especially when it comes to identifying potential connections between astronomical phenomena and terrestrial processes. These analytical methods enable not only the quantitative determination of the degree of correlation between different phenomena but also take into account complexities such as the problem of multiple comparisons, which arises when numerous hypotheses and possible connections are tested simultaneously. In such a situation, the risk of erroneous interpretations increases, as the more tests conducted, the higher the likelihood of random coincidences being mistaken for significant patterns. Therefore, to obtain substantiated and reliable conclusions, it is necessary to adhere to strict standards of evidence to avoid false alarms while simultaneously being able to notice truly significant signals if they are present. In the modern era, as humanity has created a vast global infrastructure of technological systems, numerous opportunities arise for random or casual correlations between celestial events and failures in terrestrial systems. With millions of satellites, billions of electronic devices, and countless data transmission systems operating continuously, even the simplest, entirely random failures occur daily for a variety of reasons, often unrelated to any astronomical phenomena. During periods when comet activity or solar behavior deviates from normal levels, such as during flares or solar energy emissions, such ordinary failures begin to attract excessive attention, and this heightened interest can lead to their misinterpretation. For example, a power system failure, typically attributed to equipment wear, technical issues, or improper maintenance, might, during times of increased astronomical interest, be attributed to so-called exotic influences, such as the effects of comets or solar storms, even if there is no actual connection. In such situations, education and clear communication become particularly important. Their role is to clarify how the real mechanisms of space weather impact terrestrial systems. The better people understand these mechanisms, the less likely they are to seek supernatural or exotic explanations for economic or technical failures that are fully explainable by the laws of physics and classical engineering. This idea is especially significant within our research on national and international data regarding potential connections between, for example, the so-called third originating body, and a group of 7 comets moving in a compact space. It is crucial here to strictly maintain the boundaries between verified, causally determined connections and speculative hypotheses. Only in this way can we avoid the danger of overemphasizing assumptions that have not yet been sufficiently substantiated and turning them into unfounded theories. Modern civilization has created technological complexity that simultaneously generates new opportunities and presents challenges in detecting very subtle effects, operating at or even below the threshold of ordinary observations. The high sensitivity of modern instruments, electromagnetic sensors, and measurement systems allows for the detection of weak signals that previously went unnoticed or were even unreachable for earlier generations of researchers. However, increased sensitivity also raises the risk of identifying false correlations or incorrectly determining causal relationships, as weak signals may be random and have no real connection to the phenomenon being studied. Finally, we have reached the point where the study of the influence of astronomical factors, such as solar activity or comet behavior, must be considered in the context of the psychological and cultural narratives of the modern world. People often form their beliefs about stellar influences based on myths, legends, and unverified hypotheses, which in turn can distort the interpretation of facts. Therefore, it is important to remember that the universe operates according to stable and well-established physical laws that are independent of our expectations or hopes for incredible discoveries. The Earth's response to space weather generally follows proven mechanisms, without the need for invoking extraordinary explanations. The echoes of solar storms, like waves spreading through our technological systems, are inextricably linked to effects that can be measured and analyzed, and can be traced back to their true sources. Yet, in the noise of the everyday cosmic weather, where every moment is filled with constant variability, there are often the subtlest signals worthy of the attention of modern instruments and sensitivity. These devices have the ability not only to notice weak fluctuations but also to capture subtle correlations, allowing us to trace the causal relationships of interstellar phenomena and their impact on our planet. Our research continues to be built on the fundamental laws of physics, but with each new discovery, there is the possibility of encountering phenomena that may challenge existing notions of the interaction between celestial and terrestrial processes on the scales of vast spaces and time intervals. In the next part of our contemplative chain, we will discuss the harbingers of change, which humanity often turns to as beacons pointing to future events. The entire history of humanity is replete with examples of how bright comets served as cosmic messengers, awakening in people a wide range of interpretations, from ominous prophecies to symbols of hope. These celestial phenomena, appearing suddenly and often in large clusters, had a profound impact on the psychological mindset of cultures and civilizations, shaping notions of fate, change, and cosmic order. For centuries, people have attributed special significance to meteors and luminous bodies, associating them with important events and historical changes, sometimes even with fateful shifts in power. Ancient Chinese astronomers meticulously recorded the appearance of comets, considering them as signals heralding changes in dynasties, natural disasters, and social upheavals. Their records contain notes that comets were perceived as broom stars, a metaphor that seemed to emphasize that these luminaries swept away the old and made way for a new order. Such evidence demonstrates how civilizations have always sought meaning in cosmic time, attempting to imbue unexplained phenomena with mystical or symbolic significance. In medieval Europe, interpretations of the appearance of comets often sounded like divine warnings, cosmic messages about impending cataclysms or significant upheavals in the world. One of the most famous examples was the Great Comet of 1066, which appeared shortly before the Norman landing in England and was closely associated with the destruction of Saxon power and the beginning of major changes in English society. Whether this celestial visitor had a direct influence or simply became a symbol of change remains a topic of discussion among historians, but its appearance was long etched into the memory of folklore and historical chronicles. An even more striking example is the return of Halley's Comet in 1758, coinciding with the Seven Years' War, a global conflict that altered the political maps of Europe, North and South America. For colonial Americans, this comet became an omen of independence, a sign of the inevitable break with the metropolis. At the same time, in the eyes of European scientists and philosophers, it was seen as confirmation of Newton's gravitational theories, opening new horizons for understanding the universe. This vivid coincidence shows how the same celestial phenomenon can have different spiritual and scientific interpretations, depending on cultural context, political interests, and personal views. All these historical examples convince us that the human mind and cultural consciousness are naturally inclined to connect unusual astronomical events into coherent narratives, giving them special significance that often exceeds objective randomness. In times of global crises, social upheavals, wars, or epidemics, we are in an era of rapid and constant change. When technological development occurs at an incredible pace, climate change causes concern and demands new approaches to understanding what is happening, and geopolitical tension increasingly interferes with people's daily lives, there is especially fertile ground for perceiving celestial events as signs and harbingers of change. It is in such times that people tend to seek hidden meaning in unusual phenomena in the sky, as if hoping to find answers to their anxieties and foresee future events. Modern mass media and digital media amplify these ancient psychological patterns. They use mechanisms that would astonish even our medieval ancestors, mechanisms of capturing attention and creating an emotional response. Primarily, social media algorithms collect and present content to the user that is oriented towards their interests and emotions, rather than strict accuracy and scientific reliability. As a result, dramatic videos showcasing bright comets and speculative hypotheses about their powerful impact spread much faster than scientific explanations based on long-term research and verified facts. These neural circuits, which once helped our ancestors detect patterns in the environment and avoid dangers, now respond to digital stimuli specifically designed to capture attention, retain it, and evoke emotions. Modern video editing software allows amateurs, enthusiasts, and even budding creators to craft vivid and compelling stories, combining real images of bright comets with thought-provoking music, dramatic narratives, and carefully selected visual effects that give their storytelling a professional touch. Often, such works reach the level of professional films, yet they promote ideas and hypotheses that would not withstand scrutiny in scientific journals or long-term experiments. The democratization of content production means that virtually anyone with internet access and basic editing skills can contribute to the creation and dissemination of new interpretations of cosmic events. Many independent creators often arrive at similar conclusions or interpretations, even though they do not work in collaboration. This creates an impression of broad social consensus regarding ideas that are often based more on impression and speculation than on factual data. This decentralized storytelling system rapidly transforms simple observations, such as the appearance of several comets in the sky over a few years, into much more complex and mystified stories about ingenious cosmic messages, alien visits, or impending global catastrophes. Each new retelling adds its details, connections, and interpretations, gradually steering the narrative away from the surface of verifiable facts into the realm of pure assumptions and hypotheses. In this context, the presence of 3 astronomical telescopes, or the notorious 3 ATCs, becomes an especially fertile ground for creativity and imagination. These mysterious interstellar visitors, appearing in the most unusual year of comets, lend the entire occurrence an aura of mystery and purposefulness, rather than a mere coincidence. The story seems to write itself, unfolding a drama created by our consciousness. Imagine an alien probe, in space, acting in concert with swarms of comets, transmitting a signal or message to Earth. Thus emerges an image that finally fully aligns with our psychological expectations. Such a scenario is capable of simultaneously satisfying a range of psychological needs of modern humans, explaining unusual and troubling times, attributing agency to alien or other powerful forces for random natural phenomena, and enhancing the sense of involvement in epical history. In the context of the modern information space, professional astronomy faces increasing challenges in capturing public attention, as convincingly and persuasively discussing precise orbits, probabilities, and statistics. Science, as is known, is always accompanied by a certain degree of uncertainty, which is honestly and openly presented as ranges of possibilities rather than definitive and firm conclusions. This form of expression would inspire less trust than confident statements about hidden mechanisms or meanings, were it not for the need for special responsibility for accuracy before colleagues and society as a whole. Maintaining high responsibility in scientific activity requires constant vigilant control to resist the temptation to slightly exaggerate the significance of obtained results or, conversely, to underestimate the uncertainties that are indeed present in the data. In situations where scientists acknowledge that some identified correlations exceed expected statistical probability indicators, it is important to simultaneously emphasize that the presence of a connection does not necessarily imply causation, and that these connections require further detailed analysis. Despite this, there is a risk that such statements may lead the public to not pay sufficient attention to more reliable sources that offer more accurate and definitive answers based on stricter evidence. However, this approach to research also opens up unique opportunities for educating a broad audience, which are no less significant than traditional astronomical and scientific education, because it creates a favorable ground for developing skills in hypothesis testing, conducting statistical analyses, and distinguishing facts from interpretations. By maintaining a transparent and honest distinction between indisputable facts and possible, hypothetical scenarios, we can model the real scientific process, allowing for the exploration of ideas that extend beyond conventional boundaries and flow within existing frameworks. As a result, such an investigation becomes a practical exercise in developing critical thinking, demonstrating that extraordinary claims require equally extraordinary evidence, and emphasizing the importance of remaining open to new and potentially strange but significant observations that should not be dismissed simply because they provoke doubt or seem unlikely. In a country of opinions and interpretations shaped through cultural and psychological filters, the influence of these filters on the perceived content of scientific data inevitably arises, regardless of how objectively or reliably they are presented. Thus, those seeking confirmation of the hypothesis of an alien visit may perceive ambiguous or even indirect observations as confirmation of their own theory, while skeptics, more inclined towards classical and proven explanations, will tend to dismiss even significant correlations, considering them insufficient or even coincidental to confirm the characteristics of extraordinary mechanisms of the universe's functioning. This cognitive split reflects a deeper and more fundamental question in the field of epistemology. That is, what criteria knowledge must meet to be considered reliable and sufficient for accepting unusual or even shocking claims. Various scientific and philosophical communities form their standards based on unique experiences, levels of preparation, and their own perceptions of the nature of reality. The scientific method, in turn, is based on the principle of tentatively accepting conclusions based on existing data, while remaining open to their revision and adjustment as new facts emerge. This intellectual humility is often perceived as a weakness compared to grand statements and lofty claims inherent to both sincere believers and hopeless skeptics, confident in their own dogmas. However, it is this flexibility and willingness to revise that prove to be the strongest side of science, as they allow distinguishing true discoveries from false hopes and illusions. In the history of astronomy, there are many examples where initially implausible ideas, seeming absurd and fantastical, ultimately turned out to be true due to the accumulation of new evidence and more accurate observations. There are also many theories that initially seemed convincing but over time failed and gave way to more substantiated models based on new facts. In light of this understanding, our investigation of the supposed connections between Triatlas and the cluster evidence will ultimately reveal itself, and it is important to adhere to strict standards of data interpretation. Only under this condition can mistakes be avoided and sensitively respond to signals that may challenge accepted assumptions and theoretical concepts. This is worth remembering when we undertake the study of the most sensational and provocative aspects of public speculation related to our comet research. The views and expectations generated by broad discussions often reflect humanity's natural desire to understand its place in the universe. It is this natural curiosity that needs to be channeled into questions that can objectively be answered through careful observation, analysis, and experimental verification. Ancient astronomers and mystics often paid attention to the tails of comets, seeing them as omens and portents, which can be considered not entirely incorrect. After all, celestial phenomena indeed contain important information about the mechanisms occurring in space, as well as the influence of these processes on our civilization. However, it is important to realize that such connections do not work through magic or mystical forces, but through strict physics. For a proper understanding of such interactions, modern tools and methods are needed, which far surpass pure intuition or outdated tales. The messages and harbingers we receive from space are written in the language of universal orbital mechanics and spectroscopy. This scientific knowledge allows us to decipher the messages hidden behind the brightness and movement of comets and understand what lies behind them. But before that, it is necessary to deal with the human interpretations that always surround such mysterious events. They are often colored by myths, fears, and wonder. These interpretations require continuous analysis to separate meaningful essence from artistic images and fantasies. We move on to one of the most provocative hypotheses associated with our cluster of 7 comets, the hypothesis of the extraterrestrial origin of this phenomenon. It requires courage and precise formulation, as it represents a stated assumption. According to this hypothesis, a team of 3 linked objects, named Triatlas, is an artificial probe created by another civilization, and the remaining comets are a kind of fleet or responsive group that may interact with this probe. This idea goes beyond traditional astronomy and introduces us to the realm of speculation, where irrefutable evidence is needed. However, the implications of such an assumption are so profound and vast that refusing to study it would surely render our research unscientific. It is important to understand how an artificial interstellar object would look from the perspective of established physical laws, rather than fantasies from science fiction. Such an object, created by humans or another civilization, would have to overcome many technological challenges that challenge our current capabilities. It would need to be capable of moving between star systems, and for this, the most advanced understanding of interstellar navigation is required. Traveling distances of millions or even billions of kilometers is a task with extremely complex requirements. To create a device capable of overcoming such distances within reasonable timeframes, an energy source exceeding the capabilities of modern humanity is required. Specifically, we are talking about nuclear pulse propulsion, antimatter engines, or even physical phenomena that are still beyond our scientific understanding, the so-called exotic physics. All of this underscores the complexity of the problem associated with interstellar travel. Complex navigation challenges also require solutions. The trajectory along which such a hypothetical object could move demonstrates astonishing precision, allowing it to set course for our solar system from distances of hundreds of light years. This necessitates knowledge of the positions and movements of stars over time scales of millions and millions of years, implying the presence of extremely advanced observational methods and computational systems that surpass our current capabilities. All these engineering challenges could be addressed by civilizations with high technological power, potentially leading to the development of methods and means capable of solving the problem of interstellar travel not through granting stars keen vision and magical effects, but by applying known physical principles in an extremely enhanced and crude form. Such technologies, based on the use of physics concepts that we understand on a theoretical level but have not yet fully realized, would allow the development of powerful interstellar probes, the so-called crude prototypes capable of traversing vast distances through high speeds or forceful impacts. The question is undoubtedly not about how theoretically possible such devices are, as most modern scientists would agree that they can indeed exist. The question is much deeper, whether such objects exhibit signs that allow us to distinguish artificial constructs from natural formations, as the presence and combination of three characteristics, known as ATL, serve as the key criterion for identifying them as artificial. Spectroscopic analysis plays a role as one of the most direct and reliable methods for detecting the artificial origin of these objects. By analyzing the emission or absorption spectrum, we can determine the composition of the material from which such objects are made. In the case of natural comets, spectroscopy reveals characteristic emission lines associated with water ice, carbon-based compounds, and simple molecules, the results of chemical processes occurring in the cold, outer regions of star systems. These lines arise naturally due to gravitational interactions, low temperatures, and slow chemical reactions, making them distinctive features of natural formations. In contrast, artificial probes may contain materials created by humans, such as refined metals, unique alloys with exotic properties, or synthetic compounds, those not found in natural environments where comets would originate. Therefore, high-resolution spectroscopic analysis, especially with detailed measurements, can indicate whether the probe's composition aligns with expectations for natural objects or, conversely, contains signs of artificial technologies. The detection of substances clearly created or synthesized by humans would be compelling evidence of engineering activity and would likely suggest the presence of intelligent sources in its origin, whereas spectra that fully match natural ones would refute the hypothesis of its artificial origin. Additional possibilities for recognizing artificial characteristics of the object come from analyzing its behavior and dynamics. Natural comets move along ballistic trajectories determined solely by gravitational forces. Such trajectories, although complex, ultimately adhere to the laws of classical mechanics and do not require active management. Small but measurable effects arising from sudden or gradual sublimation of gases create almost imperceptible gravitational and force changes characteristic of this type of natural object. In contrast, artificial probes may exhibit signs of active influence on their trajectory, maneuvers to change speed and direction, course adjustments, orientation changes, or active management of gas emissions. All of this indicates the presence of a control and management system, rather than simply following gravitational flows. Orbital parameters, including the sequence of changes in orbital elements, the so-called ATL elements, serve as another tool for analysis. If these parameters do not show any anomalous or unusual deviations beyond possible natural variations, it can be assumed that the object is under passive management by natural forces. Its orbit is likely determined only by gravity and slow gas release, which is characteristic of comets rather than complex engineering systems. It follows a pattern that indicates adherence to the laws of physics without signs of active, managed intervention. It is worth noting that the slightest control influences, if present, may remain hidden, especially if they are designed to mimic natural behavior. The absence of detected signals or clear signs of information transmission does not entirely rule out the possibility of an artificial origin of the observed objects or phenomena, as modern civilizations, especially those developing over interstellar distances, may employ communication methods that are currently beyond our understanding and technical capabilities. They might have employed communication methods based on frequencies we have yet to observe or used transmission methods that do not leave the usual signs of electromagnetic signals perceived by us as communication signals. The coordination hypothesis, which extends to our 7 known comets, suggests a more radical concept, that these natural objects may represent nothing less than an artificial fleet controlled externally, responding to the arrival of a so-called intergalactic transport line or network, designated as 3IATLS. According to this hypothesis, each of these 7 objects is not the result of random processes but rather a specially prepared and interconnected complex, reacting to external signals and support. Such a scenario requires our supposed beings, managing this fleet, to employ incredibly advanced technologies and interstellar mobility strategies, as well as precise coordination of actions over vast distances. To implement such an idea, each of the 7 objects must possess autonomous systems for complex navigation and propulsion capabilities, sufficient for independent and precise movement along their orbits, as well as for balanced synchronization of their trajectories to arrive within narrow time windows. This presents a challenge close to the pinnacle of engineering thought, to provide not only individual technical capabilities but also to ensure their coordination at a level unattainable by modern technologies. The scale of logistics is even more impressive, launching 7 different objects from possibly different points at different times, and then their prolonged proximity to each other over several months after years or even millennia of expeditions. Such a complex chain of events seems almost incredible if one imagines that these are not independent natural phenomena but man-made operations. Nevertheless, the orbital characteristics of these 7 traditional comets clearly indicate that they originate within our solar system. Their chemical composition and physical properties correspond to models expected for objects formed in the outer regions of the solar system, in its Kuiper belt or beyond. These objects were discovered through long-established automated sky monitoring systems, which have continuously tracked their movements for years or even decades. Such tasks were carried out by specialized observatories and automated scanners specifically designed to search for and observe such bodies. Analysis of their trajectories shows no signs of artificial course correction, no interventions, or coordinated maneuvers that could indicate their man-made origin. If we assume that these objects are indeed part of some artificial fleet, they must have undergone a complex masking operation. To appear as natural comets, they would need to conceal any signs of technological intervention, mimicking the behavior and characteristics typical of natural bodies formed in the solar system's disk. This would mean that those behind it possessed knowledge of our equipment and observation methods, as well as our scientific expectations, to design such a detailed disguise. Such a level of secrecy would require technological and analytical capabilities surpassing our own. They would need to know how we observe, analyze, and interpret cosmic objects. Of particular importance in confirming the hypothesis of a connection between events is the temporal correlation between the arrival of the 3 interstellar transport lines Triatlas and the appearance of our 7 comets. This is the most compelling argument in favor of some form of organization or coordinated action, even if the mechanism of its implementation remains unclear and directly unconfirmed. Conducting a statistical analysis of the patterns in the arrival of comets may help determine whether there is a significant relationship. The hypothesis of the existence of extraterrestrials is perhaps one of the most fascinating and at the same time controversial ideas that have intrigued scientists and laypeople alike for many years. In light of modern scientific perspectives, it, to some extent, addresses our concerns and fears related to the fact that our human society and technological achievements remain extremely vulnerable and isolated on a cosmic scale. Firstly, acknowledging the possibility of advanced extraterrestrial civilizations expresses confidence that we are not alone in the universe, but rather part of a much broader and more complex cosmic network. If such civilizations are already visiting our solar system, as the hypothesis suggests, it proves that technological progress beyond our current capabilities is possible and perhaps even already realized. Such a scenario could change our perception and understanding of humanity's place in the universe, expand the horizons of scientific research, and stimulate the development of new technologies. However, as in any field involving extraordinary and questionable claims, supporting the hypothesis of extraterrestrial origin requires the presence of impartial and convincing evidence that can credibly confirm its plausibility. In this case, the hypothesis about aliens falls into the category of extraordinary, and therefore requires equally unusual and substantial grounds to convince even the most skeptical scientists. The responsibility for presenting evidence lies primarily with those who shy away from conventional explanations and promote the theory of the artificial origin of certain observed objects. They must demonstrate signs that unequivocally indicate an artificial origin, and these must withstand the most rigorous critical analysis and scrutiny by specialists. Otherwise, any of their arguments will lack diplomatic or scientific weight. At the same time, skeptics and those who adhere to traditional approaches are not obligated to prove negative assertions, meaning they are not required to initially accept the absence of signals or signs of extraterrestrial technologies as truth, should such signals ever appear. To date, existing observational data and research are unlikely to allow a definitive conclusion about the artificial nature of the object known as Triatlas or any other members of its alleged cometary group. For now, they remain uncertain and require further analysis. Of course, the possibility cannot be entirely ruled out that some sophisticated camouflage systems, completely mimicking natural objects, may exist. However, such hypotheses imply the existence of advanced technologies, capabilities, and motivations among extraterrestrials, which we judge only by indirect evidence, thus raising many questions and requiring further proof. For now, the scientific community continues to gather new data, as each more precise observation can reveal new aspects and nuances. Enhanced spectroscopic studies, more detailed high-resolution images, and the potential detection of artificial signals or anomalies in the behavior of objects all offer hope for a deeper understanding of the situation. Professional astronomy, maintaining its healthy skepticism, does not rule out the possibility of detecting indirect signs of artificial origin, should such signs truly exist and be confirmed through systematic observation and analysis. In its work, it adheres to strict methodological rules, as the scientific approach requires the ability to distinguish real discoveries from fantasies and illusions. The general search for extraterrestrial intelligence is considered one of the most important and relevant scientific questions facing humanity today. If in the future convincing evidence were found that the object known as Triatlas, or other flying bodies associated with it, indeed possess artificial characteristics, it would be a true revolution, fundamentally changing our understanding of the universe and humanity's place within it. Such a discovery would challenge our traditional notions of the inaccessibility of extraterrestrial civilizations and resolve many existing intellectual dilemmas. Nevertheless, it is still too early to speak of confirmation. Existing evidence is insufficient. The most grimly interpreted scenarios, related to the descent of 7 comets, represent nothing more than a hypothetical situation that could occur approximately 20 years from now. In such a version of the hypothesis, a year of catastrophic disaster arrives, capable of threatening the very essence of human civilization, all under the control of forces beyond human control and understanding. This doomsday scenario turns cosmic mechanics and astronomical phenomena into something resembling a star war, where ice and rocks become destructive weapons capable of annihilating our world and completely ending the existence of the human race. It's no wonder such ideas captivate the imagination of science fiction writers and fans of incredible plots. However, when assessing real danger, it is crucial to remember the necessity of an honest and scientifically grounded risk assessment. The threats of collision with cosmic objects are generally well studied thanks to the laws of physics, which allow experts to accurately analyze the probabilities of potential collisions and the consequences of such events. When asteroids or comets approach Earth on specific trajectories, astronomers with predictive capabilities can forecast with high precision when and where these objects might encounter our planet. All calculations are conducted using astronomical and orbital mechanics, which operate based on the laws of motion of bodies in space, allowing for very precise trajectory parameters, leaving no doubt about the risk assessment of a collision. Currently, the 7 comets included in the considered scenario do not pose a collision threat with Earth during their approach. These comets, identified as Pen stars, Swan, Stereo, Atlas K1, Atlas G3, Lemon, and Neat, travel on trajectories that maintain safe distances exceeding millions of kilometers. Their closest approach to our planet occurs far beyond the possible zones of gravitational influence, making the likelihood of collision practically negligible. It is particularly noteworthy that one of the objects, known as Atlas, moves on a hyperbolic trajectory, which, upon further approach, guarantees it bypasses all significant bodies of the solar system without causing harm. Its interstellar origin and incredibly high speed relative to the objects in our system significantly reduce collision risks. This is because objects moving on hyperbolic trajectories and at high speeds cannot be captured by the gravitational forces of planets or the Sun, effectively eliminating the possibility of their collision with Earth. It should also be noted that the absence of a direct collision risk does not imply a complete lack of dangers. Increased comet activity in space entails potential threats in the form of intensified cosmic astronomical weather. The influence of solar activity, especially during solar maximum periods, can have a destructive impact on the technological infrastructure of our civilization. Electrical grids, satellite communication systems, navigation systems, and all associated technologies may become vulnerable during periods of intense solar storms, potentially leading to disruptions or system failures worldwide. However, it is important to emphasize that these dangers are not associated with moving comets, but with the activity of the solar system itself, which periodically enters cycles of maximum solar activity. 25 years is the average duration of a solar activity wave, reaching its peak approximately between 2 decades and 25 years, regardless of whether any cosmic objects are approaching Earth. The temporal connection between comet activity and solar conditions is not due to causation, but rather to the general dynamics of the solar system. It is difficult to maintain the illusion that comets cause changes in solar activity when, in fact, both phenomena occur within the broader picture of progressive cycles of solar magnetic activity. For an objective assessment of the real danger of collision, it is necessary to conduct a statistical analysis that separates significant threats from random coincidences and supposed patterns that tempt the human mind to seek causes in apparent connections. When several events with extremely low probability occur simultaneously in the world, our intuition often subconsciously tends to overestimate their significance, believing that these rare cases are somehow connected or can be combined into a single, frightening picture. In everyday life, when assessing risks, special mathematical models are used to provide a more objective view of the situation, taking into account the features of many different factors and potential interconnections. The issue of so-called multiple comparison problems is particularly important here. Situations where numerous hypotheses or connections are tested simultaneously, which in turn increases the chance of random coincidences and false conclusions. When we test many different possible connections between different types of events, such as unexpected astronomical phenomena, natural disasters, or social crises, some of the patterns found appear not because there is a real cause and effect relationship, but purely by chance. This is reminiscent of a situation where random coincidences or circumstances create the illusion of a connection that is actually absent but seems very convincing because the observation occurs at a specific moment in time. Thus, due to the psychological nature of our perception, individual events, especially frightening or unusual ones, begin to be perceived as part of a general scenario rather than as independent phenomena. For example, when a bright comet appears in the sky, it creates the impression that this is an announcement of the end of the world or the beginning of global disasters. The environment enhances the perception of this connection, combining 7 comets and 3 ATWACS into a single terrifying whole. The human mind tends to perceive such phenomena as incredibly dangerous and requiring immediate action, although from an astronomical or physical reality perspective, each of these events follows its own trajectory, governed by the laws of gravity and mechanics. Each comet, each astronomical object, is an independent movement of bodies that do not interact directly with each other and are not united into any kind of single system. The main illusion here lies in human perception, which creates a sense of coordinated, synchronized activity, whereas in reality, such interactions are absent. This happens because our brain seeks patterns and tries to find meaning in random coincidences, anchoring them in memory as something important that requires a response. The time spent observing and interpreting often turns random coincidences into the impression of interconnected events. Historical examples show how often unusual natural phenomena have been associated with disasters on Earth. In different eras, the appearance of bright comets was accompanied by wars, epidemics, famine, or social upheavals. However, thorough statistical studies have not found a significant correlation between the appearance of comets and an increase in the number of disasters on the planet. These coincidences are linked only by our psychological mechanism. We tend to perceive dramatic celestial phenomena as harbingers of disasters, especially in times when difficulties already prevail on Earth. In such moments, historians and chroniclers, recording events, emphasize not only real changes but also unusual phenomena to highlight their importance as part of the overall context. In peaceful times, such astronomical events often go unnoticed because they do not evoke an emotional response and seem less significant. Modern civilization, unlike ancient times, faces real existential threats. The main dangers, nuclear conflicts, climate change, pandemics, and disruptions in technological infrastructure, are not fiction but real threats that deserve serious measures and long-term attention. These risks are associated with understandable and studied mechanisms, allowing them to be analyzed, modeled, and strategies to minimize damage to be developed. It makes sense to focus efforts on preparing to overcome them, as knowledge and a systematic approach help reduce potentially catastrophic consequences. While alarming scenarios like the threat from a comet capable of destroying all humanity require serious confirmation, much of the attention often shifts to them, distracting from truly important issues. The allocation of resources and attention to imaginary or hypothetical threats is one of the reasons. When there is a suggestion that our cluster of comets may pose a real threat to civilization as a whole, it is important to understand that assessing such concerns requires relying on specific, measurable mechanisms, as well as quantitative probabilities and independent confirmations. Simple and vague statements about the suspicious timing of comet approaches cannot serve as a reliable basis for serious conclusions. In such a situation, the scientific method acts as a fundamental tool for conducting an objective assessment, allowing us to distinguish credible concerns based on solid evidence from those based on subjective fears or psychological biases that lack a physical foundation. For this purpose, there are special monitoring systems developed by emergency preparedness agencies, complex, multi-level observation mechanisms that not only track real threats related to space weather and the potential impact of solar flares but also evaluate them. These systems continuously monitor the situation, identify possible dangers, and provide timely warnings. Thanks to this approach, in the event of increased comet activity or heightened solar activity, especially during solar maximum periods, any potential threats to critical infrastructure elements would be detected long before they could cause significant damage. The absence of official warnings from leading organizations responsible for monitoring space factors seriously undermines assumptions about immediate dangers associated with comets. If there were a real danger, the relevant institutions would have long since warned the public and infrastructure about possible risks. Professional risk assessors, with the most comprehensive set of data, also do not note any signs of an impending emergency requiring immediate response measures. Public education on real space weather threats is an important tool. It helps shape the correct perception of the situation, clarifying the difference between spectacular phenomena that often cause fear and excitement and real dangers that require specific measures. Indeed, solar storms can harm modern technological systems, but this occurs through known mechanisms well studied in scientific research. These mechanisms can be predicted, controlled, and minimized through engineering solutions and special protective measures. In the coming year, when increased comet activity is expected, there will be a unique opportunity for observation and the acquisition of valuable scientific data on the dynamics of the solar system. These studies will not only expand our understanding of space but also bring significant benefits that far outweigh any, even theoretical, risks associated with this observational period. The main danger is that unfounded fears and panic may overshadow natural scientific curiosity and the desire to learn by understanding the complex processes occurring in space. Responsible and honest scientific communication involves acknowledging that there are areas where our knowledge is still incomplete, and there is nothing dangerous or threatening about that. Constant acknowledgement of uncertainty and the scale of possible risks helps make scientific conclusions more objective and balanced. It is important to remember that unexplored, unexplained aspects of our study of cosmic objects do not necessarily signify a threat. The universe regularly generates phenomena that challenge our existing theories and perceptions, yet do not pose a danger to humanity. Scientific development relies on a systematic approach to studying such phenomena. It allows us to avoid hasty and unfounded conclusions based on incomplete or distorted data, as well as psychological biases. As we attempt to grapple with the complex theories and hypotheses surrounding our unusual and promising year of increased comet activity, it is important to remember that to seriously consider and discuss any extreme or extraordinary scenarios, compelling and convincingly substantiated evidence is required. Extraordinary claims about cosmic threats demand, without a doubt, a foundation of most speculations based on fear lies in the inability to view the situation with a clear and sober mind, and more often, a desire to create sensation or evoke a sense of anxiety while avoiding a deep analysis of the real circumstances. Such doomsday scenarios are often painted only in imagination, stopping at vivid, dramatic images that tell more about human psychology than about real physical and astronomical processes. Their essence boils down to the fact that a person, naturally seeking patterns and explanations for what frightens them, tends to perceive rare or unusual events as signs of a global threat, coordinated attack, or inevitable apocalypse, especially during periods of social tension and stress when anxieties and uncertainties literally overwhelm society. In such moments, people may excessively exaggerate the significance of random coincidences, attributing symbolic or even predictive significance to them. At the same time, the universe operates in strict accordance with the laws of physics and astronomy, which remain indifferent to human fears and expectations. All celestial bodies and phenomena follow predetermined laws of nature. For example, comets move along gravitational trajectories calculated with high precision thanks to modern astronomical models and observations. Their orbits are determined by mutual attraction and gravitational dynamics, which can be accurately predicted based on mathematical calculations. Similarly, solar activity, manifested in the form of flares and coronal mass ejections, follows magnetic cycles that have been studied for a long time, allowing predictions based on statistical models. Everything related to the effects of space weather, electromagnetic processes affecting Earth systems, is also well measured and modeled thanks to modern technologies. Thus, the cosmic clock, whose rhythm is set by the patterns of physics, continues its precise course regardless of the dramatic stories that often arise in our minds when we see rare bright phenomena. Understanding these patterns brings not only practical benefits, it provides a sense of confidence and satisfaction because it allows us to look at the processes occurring in the universe without fear and panic. Instead of wasting time and energy on fruitless worries and speculations about the end of the world, a person gains a deep understanding of the mechanisms of the cosmos, which significantly broadens their horizons and strengthens mental resilience. This knowledge allows even the most vivid and alarming astronomical events to be perceived as part of a universal order that can be predicted and understood, rather than as signs of an impending catastrophe. Part 14. The main idea of this section is disguise and hidden threats. Perhaps the most complex and intriguing hypothesis in the context of conspiracy theories related to our phenomenon of the 7 comets is the assumption that we are witnessing some initial stage of an extraterrestrial invasion. And it is being concealed under the guise of natural astronomical phenomena, such as the appearance of comets. In this scenario, it is assumed that a powerful ship or fleet of space objects, for example, a ship named Triatlas, serves as a command center, directing operations for observation, reconnaissance, and possible preparation for the capture of our solar system. These objects, according to proponents of this hypothesis, are disguised as ordinary comets, allowing them to approach planets and moons unnoticed, conducting reconnaissance, gathering information, and preparing for possible aggressive actions. Such an operation would require a level of technological development that surpasses even the boldest fantasies. Each alleged probe is a complex technological device capable of perfectly disguising itself as a natural comet. Its tasks include imitating spectroscopic characteristics, behavior during evaporation, and orbital dynamics so that the science and technology of Earthlings cannot distinguish it from a real object. Such deception requires a deep understanding of spectroscopy and the analysis of the chemical composition of comets. The camouflage must be so perfect. Creating an artificial imitation of a comet capable of convincingly replicating all its behavioral reactions and features would require the most complex engineering activities and precise tuning of numerous systems. One way to recognize such a fake is by analyzing the light curves and brightness variation patterns characteristic of real comets. In nature, comets usually exhibit smooth, gradual brightness fluctuations, often interrupted by random outbursts. These outbursts occur when new layers of volatile substances are exposed on the comet's surface, causing a temporary increase in reflected light. At the same time, rotation periods recorded by brightness changes indicate the natural rotational motion of the body, reflecting its own dynamics and gravitational interactions in space. If our 7 known comets were artificial structures created by humans or another highly advanced civilization, their light curves would ultimately need to indicate signs distinguishing artificial regulation from natural mechanisms. It is the artificially controlled rotation, pre-calculated and stabilized brightness changes, and other signs of actively controlled behavior that should become noticeable with constant photometric observation. Under such conditions, any regularity or anomaly arising in the brightness function could become the key to recognizing artificiality. An even more fundamental problem for masking such objects is their orbital behavior. Each of the 7 comets known today follows a unique trajectory that can be traced back millions of years by analyzing their gravitational evolution. Such orbital histories bear the imprints of the regions of their formation in the original conditions of the solar system, interactions with planets, and gravitational perturbations that shaped their current trajectory. Creating artificial objects whose orbital motion would be completely indistinguishable from natural comets would represent an extremely complex task. This would require launching them from specific regions in specific directions so that their trajectories exactly match those expected for objects formed in the outer parts of the solar system. Such conditions require special logistics and large-scale space operations, which are difficult to achieve even at interstellar distances and within short human timeframes. Moreover, the discovery history of our 7 comets is well documented in entire archives of astronomical observations and programs carried out over many years or even decades. Archives of such initiatives, like the NT Lemon and Atlas projects, contain detailed information, data on each discovery, the circumstances of its appearance, subsequent orbital calculations, and arrival time predictions. Scientists use this information to test hypotheses about the nature of comets. If these objects had recently appeared in orbits, suggesting a possible artificial nature, their appearance would have been recorded suddenly and would have immediately attracted the interest of the scientific community. However, all data indicate a gradual and apparent disclosure of information about them, consistent with the assumption of their natural origin. This is exactly how natural comets would behave upon reaching the inner solar system. An additional aspect that allows for the detection of artificial origins of objects is the means of communication and coordinated interaction. Imagine a group of 7 objects acting in concert, along with a command spacecraft, exchanging information during their movement. To maintain coordinated operation, constant data exchanges via radio signals, laser communication, or other electromagnetic transmission methods would be required. Such signals, passing through space and reaching Earth, could easily be intercepted by specialized monitoring systems. This continuous exchange of information would become important evidence of artificial control and coordination, which in turn would help detect any hint of an artificial origin of an entire complex of objects moving along predetermined trajectories. The community engaged in the search for extraterrestrial intelligence employs modern radio telescopes and innovative technologies to continuously monitor significant portions of the sky to detect possible signs of artificial activity. One of the main initiatives is the Breakthrough Listen program, along with research projects related to the legacy of the Arecibo Observatory, as well as numerous other scientific programs and studies. All these efforts aim to systematically identify those signals that could originate from technological civilizations whose communication methods require coordinated efforts between various elements of a presumed incursion or development. However, despite all the advancements in the capabilities of modern instruments and search methods, the absence of detected artificial signals related to our system does not fully guarantee that contacts are not occurring at all. This is because advanced extraterrestrial civilizations, possessing sufficient technological achievements, may use transmission and communication methods beyond the current human understanding and possible means of detection. Nevertheless, the requirements for signals to organize interstellar operations or coordinate foreign objects at solar system distances generally imply the presence of sufficiently powerful energy sources and repetitive transmission patterns that can be detected by appropriate instruments. The strategic logic of scenarios involving covert invasion faces fundamental questions about the cost-effectiveness and justification of the risks associated with smoothly organizing such operations without obvious signs. In particular, the question arises as to why highly advanced civilizations, possessing interstellar travel and the ability to carry out complex technological projects, would choose such complex and convoluted covert methods when direct approaches and open communication methods would seemingly yield faster and more reliable results. After all, a transparent and easily detectable presence could ensure minimal costs and increase the chances of success. In practice, the use of camouflage techniques and disguised means provides strategic advantages only in cases where the target side has substantial defensive capabilities and detecting their behavior is critically important. But when it comes to civilizations technologically superior to ours, the resource costs needed to create and deploy a complex of multiple sophisticated camouflage probes and a command ship would exceed the economic potential of the entire human civilization by tens or even hundreds of times. In such a situation, the meaning of such expenditures becomes questionable, as powerful technological advantages would have earned such civilizations, rendering any tactical or strategic attempts to hide irrelevant. Moreover, scenarios based on the idea of invasion imply the presence of hostile intentions, which raises additional doubts, as there is no compelling evidence presented to confirm aggressive or threatening behavior from the detected objects or their characteristics. None of the observed objects, including those moving along trajectories that will take them out of the solar system and prevent the establishment of a permanent presence, demonstrate unique or superior capabilities beyond what could be expected from natural bodies or random cosmic objects. It is interesting to note that the popularity of invasion scenarios is largely explained by contemporary internal fears and concerns related to technological upheavals, increased competition for limited resources, and the diminishing human initiative due to progress surpassing our capabilities. These fears easily find reflection in the interpretation of unusual astronomical phenomena, which may be perceived as manifestations of forces operating beyond human control or understanding. However, despite the appeal of such hypotheses, they remain speculative and unconfirmed by scientific data. Established scientific evidence indicates that any observed astronomical objects, even the most unusual and mysterious, should be explainable in terms of natural processes. The hypothesis of extraterrestrial civilizations as the source of observed phenomena requires compelling evidence. In other words, it is necessary to find signs of artificial origin, such as coordinated behavior. Modern spectroscopic analysis allows for the precise determination of the composition of unexplained objects, characterized by properties that correspond to natural formations formed under conditions of the solar system. These studied materials and structures demonstrate spectral indicators similar to those observed in meteoritic bodies, asteroids, and other natural bodies included in the organization of our star system. As for orbital characteristics, they fully correspond to theoretical expectations for celestial bodies undergoing dynamic and gravitational evolution over millions of years, further confirming their natural origin. Models describing the possible behavior of such objects do not reveal any signs of active intervention or control by external or artificial forces. All observed variations fall within the scope of probable statistical coincidence and do not raise concerns about the presence of any intelligent or intentional influences. In other words, to date, there is no evidence capable of confirming the presence of any artificial signs. It is important to emphasize that the responsibility for providing convincing arguments lies with proponents of hypotheses that go beyond conventional explanations. Efforts to demonstrate such signs, in their opinion, must be supported by rigorous and consistent evidence capable of withstanding meticulous critical analysis, as this is the only way to eliminate the likelihood of errors or subjective interpretations. The absence of compelling evidence does not directly refute the hypothesis of possible artificial origin, but on the other hand, the current body of observations and research clearly inclines the scientific community towards more traditional and conservative astronomical explanations. For a long time, professional astronomers have been systematically monitoring all unusual and atypical objects that come to their attention in the search for signs of extraterrestrial civilizations or artificial origin. This process is aimed at detecting any characteristics that might indicate creation or control from outside, as such parameters and properties could serve as keys to solving the mystery. The established practice in the scientific community involves strict adherence to existing evaluation protocols, which includes the use of standardized criteria to distinguish between likely and unlikely discoveries, as well as the application of scientific methods to separate genuine signs of artificial origin from random or natural anomalies. Not every unusual phenomenon or characteristic is immediately considered evidence of extraterrestrial intervention. However, such systematic measures help minimize the risk of erroneous conclusions and ensure that any potential sensational discoveries are backed by sufficient and reliable evidence. Research continues as new technological tools and more precise observation instruments allow for deeper analysis of the characteristics and behavior of discovered objects. Modern methods enable the acquisition of more detailed information, the study of dynamic changes, and the identification of even the subtlest signs indicating possible artificial origin. Time works in favor of scientists. As observation technologies improve and more data is accumulated, the presumed unique signatures and signs of artificial origin should become increasingly apparent and convincing. It is crucial for the scientific community to remember that it is precisely these observations and verifications that form the foundation of the entire theoretical base and further hypotheses. Scenarios devised in the realm of science fiction play an important role to some extent. They help expand the boundaries of possible concepts and prepare minds for unexpected discoveries. Moreover, such scenarios serve as valuable tools in modeling potential scenarios of extraterrestrial contact or technological intervention. However, despite the value of such imagination and creativity, they must not become the basis for claims that contradict existing scientific data. Entertaining depictions and hypotheses should not replace rigorous analysis and verification within the framework of scientific methodology. When observations and experiments do not confirm the hypothesis of exotic technologies or artificial structures, hasty conclusions should be avoided, and they should not be incorporated into the general framework of understanding. The universe offers us plenty of genuine puzzles and mysteries, which are sufficient without months of intense research, meticulous tracking of orbital trajectories, scrupulous analysis of statistical probabilities, and thorough examination of all possible connections linking the three atlases and our unique parade of 7 comets gradually form a clear picture. As a result of these multi-stage efforts, a conclusion emerges that is both astonishing and inspiring. We have witnessed an extraordinary natural phenomenon that should not be perceived as the result of any form of exotic coordination or external intervention. This phenomenon is a coincidence, within which an entire swarm of 7 comets this year represents a genuine statistical cluster that attracts special attention. Such concentrations are rare, and it is their rarity that creates a sense of special significance, turning the dynamics of the outer solar system into a living demonstration of its unpredictable beauty. 6 specific objects, Pan-stars, Swan, Stereo, Atlas Codon, Atlas Gris, Lemon, and Neat, follow their orbits independently, shaped by gravitational forces and mysterious cosmic processes long before the dawn of human civilization. These trajectories emerged millions of years ago, and it is within this vast span of time that the mechanisms forming their current positions were set, ultimately leading to such an apparent and vivid convergence. Attempts to consider what is happening here and now as mere coincidence overlook the profound beauty and scientific value hidden in this complex picture. In reality, the universe, like an artist, has orchestrated a celestial celebration, creating a unique festival that opens unprecedented opportunities for comparative astronomical research, the popularization of space science, and deepening our understanding of the dynamics of the outer boundaries of the solar system. It is worth emphasizing that, although technological and astrometric events may seem random, their scientific and cultural significance extends far beyond mere coincidence. Simultaneously, an additional layer of wonder is formed. the appearance of a third Atlas, referred to as an interstellar guest in our system. This object became the first well-documented interstellar body to enter our solar system, exhibiting behavior reminiscent of a comet. It contains ice and dust formed in distant worlds beyond our star system. These interstellar travelers have traversed millions of years of interstellar journeys before arriving here. Now, their ice and dust are gradually evaporating under the influence of our sun's heat, forming characteristic tails that reveal the alien chemistry, a unique testament to their origin. Interestingly, the temporal connection of these interstellar objects with comet stream activity over the past year remains under close scrutiny by researchers. Although most data currently points to coincidence rather than causation, it still leaves room for contemplation that sometimes nature organizes patterns and symmetries through purely natural processes. Such coincidences fill our minds with the understanding that in the vast universe, the significance of events and random coincidences sometimes coexist without requiring mystical explanations. Does this mean that everything happening is pure chance? No, rather, it is all part of a grand cosmic spectacle, where every element, even a random one, fits into the overall picture. Emphasizing this sentiment, it is worth noting that the study of orbital relationships, behavioral characteristics, or temporal correlations between different objects has not revealed any anomalies or features that exceed statistical model predictions. All studied parameters fall within the range of what can be predicted based on known gravitational forces, solar heating, and other physical processes. In other words, each comet is a whole story told by nature about the formation of the outer boundaries of the solar system, the gravitational perturbations that might have altered its orbit, and the comet's response to increasing solar radiation as they approach. Researchers of cosmic phenomena have a unique opportunity to study in depth how different compositions, sizes, and orbital geometries of comets react to similar conditions of solar heating. This approach allows us to expand our understanding of the physics of these mysterious cosmic bodies using methods that are wholly or partially unavailable through simple observation. In particular, the activity of our star, reaching its peak, manifests intensely as a bright spectacle, turning comet parades into truly mesmerizing displays. This period of solar activity creates unique natural conditions, becoming a kind of experiment in studying space weather. Coronal mass ejections accompanying the active phases of the solar cycle not only threaten the operation and safety of our technological infrastructure but also give rise to dramatic scenes in comet tails and unstable plasma processes, making their observation and photography especially thrilling. During this dynamic period, photographers and astronomy enthusiasts worldwide capture these manifestations of cosmic celebration with stunning detail, creating rich photo archives. These collections can become an essential resource for scientific research, supporting and complementing professional data for many decades. The modern democratization of astronomical imaging technology makes it possible for hundreds of observers to participate, who, with accessible devices, contribute valuable information, expanding research capabilities beyond the resources of large scientific institutions. This mass involvement, stimulated by our attention to the 7 comets, shows how unusual astronomical events can ignite interest in space sciences and promote the development of critical thinking skills in a broad audience. By analyzing unusual manifestations and claims based on available documents, scientists gain unique educational opportunities. This approach demonstrates how properly applied scientific methods help separate well-founded hypotheses and facts from speculation and unproven assumptions. Despite the absence of fantastic or exotic explanations, new perspectives for future discoveries are not excluded. Continuous monitoring of astronomical events can reveal subtle interconnections and patterns that may currently remain beyond the reach of current observation methods. More data and new technologies in analytics allow for the detection of subtle signs that were previously only a dream. Science advances through the gradual improvement of measurement accuracy, the development of analysis and modeling methods, which helps uncover previously hidden phenomena and connections. Regarding the period of the 25th era, its characterization as a statistical cluster of objects can become a valuable source of information about the long-term dynamics of the solar system. Such analysis can reveal patterns over time that exceed the boundaries of human history, allowing us to understand whether similar events occurred in the past or if they repeat in predictable patterns. Possible causes of such periodic clusters may include gravitational resonances, solar cycle effects, or other cyclical mechanisms influencing the timing of comets and other celestial objects entering our observation area. Professional astronomers will continue to systematically observe all unusual objects, analyzing their characteristics to identify signs of potentially artificial origin or exotic physical processes. The public community takes these issues seriously and applies strict standards and criteria when evaluating unusual phenomena, distinguishing real anomalies from statistical fluctuations and random spikes inherent in large datasets. This is one of the important tasks of modern science, to maintain vigilance and objectivity to foster the development of our knowledge about the universe and its mysteries. Our research goes far beyond the simple question of the connection between the third astronomical pole and traditional comets traversing the expanses of the solar system. It illustrates how rigorous and methodical scientific inquiry can consider even the most exotic hypotheses while avoiding the pitfalls of speculative fantasies that often give rise to such ideas in popular culture and public imagination. In the modern era, it is crucial to maintain a balance that combines an unquenchable interest in new discoveries with healthy skepticism. This balance is becoming increasingly relevant because social media algorithms, rapidly spreading sensational claims, often do so faster than scientists can prepare a comprehensive analysis, evaluate them in the context of existing data, and understand their true significance. In such a situation, the scientific community bears a special responsibility. It must strive to provide the public with the most accurate, verified, and honest information. At the same time, it is important to acknowledge the uncertainty and limits of our knowledge, without trying to compete with content created for entertainment and sometimes based on exaggerations or premature conclusions. The experience related to the anticipated comet of 2025 largely demonstrates how the human desire to find patterns and assign meaning to observed events can transform entirely objective astronomical phenomena into subjective stories about the mysterious significance of the cosmos. This transformation is not necessarily a problem. The engagement in the search for meaning, experiencing a sense of wonder, even in the most ordinary cosmic events, are characteristic features of human culture that have inspired people throughout history. However, it is important to make a clear distinction between actual observations and the interpretive frameworks in which these observations are analyzed. Modern astronomical tools today provide unique opportunities to explore both genuine anomalies and apparent patterns, which are often manifestations of ordinary statistical fluctuations. At the same time, these tools allow us to uncover cosmic-scale phenomena, often surpassing human imagination, without resorting to exotic theories. They show that reality often exceeds the boldest creations of human speculation. As we conclude our exploration, there is a sense that the cosmos has become both more understandable and more mysterious than one might infer from popular stories and myths. This is because the universe moves and functions according to fundamental physical laws, which can be derived and understood through precise observations and scientific methods. These laws naturally give rise to phenomena that challenge human intuition, stimulating our further quests and investigations. The message that may be contained in messages like those coming from the Swarm of 2025 is that the existing astonishing manifestations of the universe are sufficient without resorting to fictional or exaggerated theories about mysteries and wonders. In this context, the appearance of 7 independent comets, brought about by natural astronomical processes, converging in their behavior and characteristics, is entirely natural. While an interstellar visitor makes its first and possibly last passage through our solar system, this is a unique and remarkable cosmic coincidence worth noting, as it occurred at a truly special time. This experience enriches not only our knowledge of astronomical phenomena but also develops crucial critical thinking skills that are useful in all aspects of human life. The ability to distinguish between correlation and causation, to evaluate claims according to strict standards of evidence, and to maintain a genuine sense of wonder while demanding a rigorous scientific approach. All these create intellectual tools that can serve society far beyond the study of comets and stars. Ultimately, their significance lies in the fact that, despite all the achievements of science, the universe continues to remain mysterious and inspiring, offering such a rich field for exploration and wonder that no additional marvels are needed for us to feel awe. It is thanks to these natural phenomena that future generations of researchers may look back on the year 2025 as a turning point in the history of astronomy, a period when the latest observational tools and the development of social networks merged to transform daily astronomical discoveries into cultural events that resonated with millions of people worldwide. These achievements not only enabled a more precise and enriched perception of the cosmos but also led to ordinary observers, untrained by the scientific community, actively participating in discussions about evidence, the likelihood of events, and the nature of scientific knowledge itself, expanding the boundaries of understanding and engaging a vast number of curious and passionate citizens in scientific dialogue. It can be said that the ultimate conclusion of this epochal interaction is that it is human curiosity and an analytical mindset, rather than any external cosmic coordination or mysterious alien contacts, that highlight the most remarkable aspects of this entire experience. In this process, tools and methodologies were created that allow for the exceptional precision in identifying interstellar visitors, calculating orbital parameters with extraordinary accuracy, and critically evaluating claims based on weak or ambiguous data by applying rigorous statistical approaches that confirm their scientific validity. These technological and intellectual achievements deserve no less attention and recognition than any bright and impressive phenomena seen in the sky, for they expand the horizons of our knowledge and allow us to better understand what lies beyond the boundaries of visible phenomena. Although the universe does not directly send us messages in the form of coordinated arrivals of comets or alien artificial objects, it constantly provides us with new opportunities for discovery, prompting us to carefully observe and analyze the surrounding cosmos. Such observations, in turn, are rewarded not only with new facts but also with a deeper understanding of our own cosmic environment, its laws, and cycles. The exploration of space always brings us back to the beginning, namely, to the wonder of unusual phenomena, to respect for rigorous scientific analysis, and to gratitude for the infinite generosity of the universe, which holds enough mysteries and secrets to stimulate human curiosity for millennia. Hypotheses are tested, evidence is carefully evaluated, and a sense of wonder remains untouched because it becomes the driving force for future research. These discoveries and achievements made today remain a reliable foundation for the scientific efforts that await us beyond our current observational horizons, horizons that expand with each new glimpse into the depths of space, with each new investigation unveiling new mysteries of the universe. In this process, the ongoing great game of mind and curiosity, lies the infinite beauty and value of the human quest.